And then when you're ready, go ahead and go to learn.nvidia.com/DLI-event and put in this code. And that should bring you to the start page. So you should see something like this when you get everything ready. Okay? And I don't know if anybody wants to take a picture of this. Yeah. I tried to remember to, print out some little things for people who are coming in late, but, life happens. Who uses a printer anymore? All right, we'll give everybody a few minutes to get going. I'm actually going to get mine started as well. So this is the course here. I'm going to hit launch here, and that's what's going to bring up my notebook. So this is what you should see when it opens. I'll try and make this a little bit bigger and give you a little bit more real estate over here. So I'm just going to keep this up a little bit longer so that people can get set up. And we do have two amazing TAs here who are here to help. Here's Keith in the purple back here, Sergey here in the black. Keith is our Director of Engineering for the CUDA-Python team, and Sergey is on product for nvmath-python. And so we're all three here to help you. Leo Feng should also be here too. He's also one of our technical leads on CUDA-Python. So you're talking to the people who make your life hell. Bring us what you got. So yeah, just anywhere that's open. We're going to give everybody a few minutes just to catch up. And if you are having any problems, please raise your hand and one of us will come over to help you out. And once again, for whoever came in, this is what you should see when you have everything up and working. right, how many people are not set up yet? I mean, besides the person that just walked in. Okay, we'll give it a few more minutes. How about now? How are we doing? Anyone stuck? Excellent. All right. Within 10 minutes. Oh, one more. Hang on. All right, sounds like everyone's doing okay. Just one more check because I know that sometimes it takes a minute or two. Awesome, but we got through this in the first 10 minutes, so we're doing great. All right, once again, if you don't see this page, notify one of the TAs and we will get you going. But go ahead and get this started. It's going to spin up in the background. We should have some hot labs that are already reserved for you, so it should spin up pretty fast. If not, I'm going to go through a few slides before we get started, and that'll be plenty of time for it to spin up, basically. But what you'll see is this when it's ready. Okay? All right. So coming back over to the slideshow. So the most important thing, this is 4 hours. I don't expect y'all to sit in these seats for 4 hours. So we're going to take a couple of breaks. So I'm going to try and shoot for 9:15 for our first break. Our second break at around 10:30, and I do want to stop about 15 minutes early so we can do questions, kind of point you to a few resources, things that you might want to check out beyond this. Obviously, we're going to try and cram a ton of information into 4 hours, and so it's going to be like drinking from a fire hose. And so there's no way you can become a complete, expert in CUDA-Python within 4 hours. So definitely want to get you set up so that you know where to go from here. And so I'm going to try my best to stick to that schedule. But before we get started, I do want to orient you just a little bit so you understand a little bit better about what the Accelerated Python ecosystem looks like. And so when we talk about the CUDA ecosystem, we have everything that goes, you can think of it as part of these layers. And so everything down to the hardware, so this is where we have our GPU is all the way down at the hardware side. On top of that, we have our core runtime. So that's where you have like your CUDA runtime that is I'm sorry, are you okay back here? Okay, I think we're good. We have a core runtime, so we do have the CUDA runtime that sits on top of the hardware, and that's what's going to execute everything, so you do have that runtime engine going. We have language feature support, device parallelism, up to math libraries, array interfaces, domain libraries, and frameworks. And when I talk about these, they all build on each other. So as you go further and further down the stack, we start talking more and more about the C++ libraries. CUDA was originally written in C, C++, and that's where all the runtime libraries. However, what we're doing on the CUDA-Python team is we're trying to make Python native ways to be able to interact with the CUDA runtime. So instead of having to walk into a CUDA-Python tutorial and the first thing they tell you is how to write a C++ kernel, you actually get to talk about Python. So, and especially in a way that people understand it. But as we move from the low levels up to the high levels, we do abstract more and more pieces of the CUDA environment away from you. So things like memory management, thread indexing, things like that start getting abstracted away as you move up these libraries. And so what's nice about this is that you go all the way up to something like a framework. I would consider PyTorch a framework where you have access to low-level CUDA internals, but at the same time, it has a very nice, very friendly, relatively friendly interface for you to be able to get your work done, but also to be able to interact with CUDA. But there are many, many, many paths to success within this ecosystem. It can get a little bit daunting when you start realizing how many libraries we're talking about and how they all work together. So what I'm really trying to do in this particular course is show you where are those really popular points of entry to be able to understand how to use CUDA from Python, and then how to interact with those and where to go from there. So that's kind of what we're going to try and do here. So I was talking a little bit about these different exposures of the CUDA ecosystem. And so this goes all the way from hardware up to domain libraries like I had on the other slide. And on the purple side, those are the C++ libraries that have been around for a long time. The C++ side of the equation has been, it is tried and true. It's been around for a long time at this point. The Python side, we have a little bit of catching up to do, which is great because it gives us all jobs. But you can see that there are pieces of this equation that are currently missing. We have a lot of different libraries that are in beta right now that fill in these gaps, and I'll talk a little bit about that, I think, later after we get through this tutorial. But just kind of understand that the CUDA principles, like how to use CUDA and what CUDA is doing, are universal, regardless of which level you're coming at it from. And so if you do understand the core concepts behind CUDA and how the architecture works, that would be able to, you'd be able to work at any one of these layers and understand how to use it. That's fully transferable. But depending on how you're writing your application or your library, we want to be able to support both, right? So library developers are probably going to be more interested in low-level libraries, and then people who are writing applications probably higher-level libraries. But in either case, you should be able to get to all CUDA internals from there, okay? And so this particular tutorial, we're going to focus here. So this is where we're going to stay. I know that some people really want to talk about kernel authoring and things like that. Stay tuned, we will have that for sure in the future, but there are a few libraries that are still in beta. This fall we should have a few releases that'll make things a lot easier for people. And so this is where we're going to stay. All right, but I do also want to talk a little bit about the, I'm sorry, was there a question? The question was if the PowerPoint was available after. I will make it available. Okay. This is actually probably a good time for me to just go ahead and bring this up. So this is my GitHub repository. It's the Accelerated Computing Hub. It's under the NVIDIA GitHub organization. And this is where I put everything. So all of the information for this particular tutorial is actually here under GPU Python tutorial. So you have access to all of these wonderful notebooks and everything. I'll put the slides in here with the notebooks. But there's also this really great, I mean, I'm obviously very biased here, but I think it's great, Accelerated Python user guide that I wrote that has a lot of information that you might find interesting. And the reason I bring these up is because, you know, a lot of people ask about like, what are GPUs good for? What does parallelism mean? So it goes all the way from the very beginning. So even talking about, you know, the pros and cons of GPUs versus CPUs, what each one is good for, because GPUs aren't good for absolutely everything that you want to do. Like, you know, you have a whole bunch of operating system calls, probably not the right paradigm for you to be working in. And so just kind of keeping this in mind. And actually, if you want a, I have a, it'll pop up here in just 1 second. Apparently, it's taking a bit of time. Come on, don't do this. I have a QR code in here that apparently doesn't want to load. Anyway, I'll come back to it, but there is a lot of information in here. And so, yeah, everything from this tutorial, I'll make it available in here. And also, just, you know, I have a pretty long history with open source. I run this as an open source project. You'll probably see that there are over 30 contributors to this repository. So if you do see things that you don't like, if you have issues, if you want to contribute, anything like that, don't feel bad about opening an issue, opening a discussion, or even submitting a PR, because I do review them as they come in. Okay. So back to the presentation. Did our Wi-Fi go down or something? Okay. 3 sound checks. Everything worked out beautifully. Just, you know. Okay, I'm not sure what's happening here. I'm going to stop this. See if that helps. Okay, awesome. Okay, so we have several different strategies that we use from the Python side on how we're going to interact with CUDA. So at the top of this, you see the first swim lane is the zero code change acceleration plugins. These are the ones that you're not even really aware of. So things like cuDF.pandas, for example, actually kind of, overloads the import system, and if it has cuDF available to it, it'll dispatch there. If it doesn't, it's going to dispatch to pandas on your CPU. This also includes like the NetworkX backend, so the NX-cuGraph backend for NetworkX. That one, it is just plugged in, so there's one backend available through cuGraph. There could be other plugins that are available there for other backends as well. And so these are architected in such a way that kind of hides whether or not you're dispatching to CPU or GPU. You have the hybrid approaches. So the next one, the hybrid CPU, GPU libraries, PyTorch is going to be in this one. So is XGBoost and TensorFlow. Those are the ones where they will both, they're going to execute on either your CPU or your GPU. You just specify which backend you want to use, right? Next one, we have the GPU Python library. So this really, I would mostly thinking about Rapids. So we have a few different Rapids tutorials. I know one of them is in parallel with this one, but we also have another one tomorrow afternoon. But the Rapids libraries are, if you're familiar with NumPy and Pandas and scikit-learn, those type of libraries, they are complementary to that. So on the Rapid side, if you're using something like Pandas, you use cuDF. So there is an accelerated version of data frame library with the same sort of syntax and API that's available over on the Pandas side. So it should look very, very familiar to you. You're going to get some practice working with that during our tutorial, in fact. And then from there, moving down to the C++ CUDA high level, this is where we start getting down into like the C++ side of things. Like I said, where we're going with the CUDA Python team, we don't necessarily want Python developers to have to write C++ in order to get the performance that they want out of CUDA. And generally, when you think about moving down those layers of abstraction I was talking about, the closer you're getting to C++, you would also imagine that that's where all of your performance is coming in. However, what we're trying to do on the CUDA Python team is make it so that we have the abstraction layers, you have native Python native ways of interacting with CUDA without losing any performance, in fact. So that is kind of where we're headed at this point. And then the CUDA toolkit. Nothing works without the CUDA toolkit. And this is going to include all of your underlying different kernels, math libraries, things like that. So one of the things I also mentioned to people is that writing kernels can be a bit of an art. It's absolutely available to you, but maybe not necessarily the main way you want to spend all of your time. And we do have a lot of libraries that implement a lot of different kernels that have been implemented for you really by NVIDIA employees or people who've contributed them and have already been tuned to be very, very fast. So a lot of times you can find what you're looking for in one of these libraries without having to re-implement it yourself. So I'm definitely in that category of people who will beg, borrow, or steal before I write my own code. So I would always check those out first. All right. And I mentioned Rapids before. I do want to point out to their GitHub repository. So Rapids is open source. It's another thing where you're able to interact directly with the Rapids team if you choose to. So feel free to open issues, questions, reach out, bug reports, things like that. There's a lot of really good information on the Rapids website as well. And so I highly recommend looking at it. And so with CUDA Python and Rapids, there's a lot of overlap, obviously, and this tutorial is really geared more towards like the Rapids side of this hierarchy. And so I just want to point out, though, once again, all of those concepts are universal. So they do translate as you move back and forth through here. Also, I do want to mention that Rapids has an amazing deployment guide, which I think is really great on their website. So I definitely recommend looking at that because deploying apps is always a bit of an art in Python, and which luckily is not part of this tutorial. And but there's a lot of really great advice on there. And so I just wanted to point out some of the things that We talked about here, so with cuDF.pandas, we talked about how this is going to kind of overload your import system. And here, you can see this, this directive here, the load extension, cuDF.pandas. We're still importing pandas as PD here, but we are actually dispatching a cuDF if it is available to us at that point, because we've actually overloaded that portion of the import system. So being a little bit careful here just to make sure you understand where your calls are going to. We're gonna have a whole lot of, hey, is this executing on my CPU or GPU questions as we go through this tutorial. But this is one of those where you don't have to change any of your syntax and you just get that acceleration almost for free without having to change much of your code. And we have several different examples of that as you go through this. And in fact, a lot of the advice that I give people when I stay for sprints and things like that, which I will be here for sprints, by the way, if you do want to try accelerating your code, we'll be here to help out with that. But if you're writing something in NumPy, just switch it over to CuPy and don't change anything and see what happens. That's actually a really good way to get started. And then you can see like, okay, how much acceleration do I get from just that one step? Can I take it even further? All right. And here you can see even just with that one change, the zero code change, that you have 150 times faster with nothing changing otherwise. And so this is exactly why we want to move in this direction, so that these are the syntax that you've all worked with, that you're familiar with, APIs and libraries that you've worked with for a long time, without having to do anything, just immediately get that acceleration in there. Because that's the whole point of using a GPU, right? If you have a whole lot of data and you want to do massively parallel processing on it, this is the way to do it. All right, we're also going to talk about numba quite a bit. So you probably, numba is one of those projects that has been around for quite a while. So you can almost think of it as like a Python to LLVM translator if you want to. And this does work on your CPU as well as on your GPU. Numba CUDA has actually split out from numba, so this is like a separate project at this point. And this one, I want to make sure that you're aware of that because some people do get confused between the two. And so we're gonna go through this one quite a bit, and you're gonna do some exercises with numba here. So we'll talk more about that in a bit. And then here, I'm actually gonna go ahead and skip this and just move on to the exposures of the CUDA ecosystem again. I mentioned that there were these different areas that we're filling in. So we want to make sure that we are creating a holistic Python ecosystem, a native way for Python users to be able to interact with CUDA. And so we can't do that without having these other pieces in here. So things like nvmath-python, which Sergey is on the nvmath-python team, CUDA.parallel, CUDA.core, numba CUDA, CUDA.cooperative, nvmath device. All of these different libraries are filling in that gap that we see. And so these are all available, by the way, in beta right now, so you can get them from PyPI as well as on CondaForge, and you can play around with them now. We'll be adding them to tutorials probably this fall, as we have a bunch of things that are coming out around that time. Okay, I would be completely remiss if I didn't talk a little bit about developer tools. So. As Python developers, I know we are not the best people at using our tools. I've been doing Python since 1998, and I am proud to say that I mostly use print statements to debug everything in my Python code. But it's a little bit harder on the GPU just because of the fact that, print is an operating system call, it goes through your CPU. Okay, so if you want to see what's going on your GPU, sometimes you got to be a little bit more open to using tools. And so the Nsight, we have a ton of different Nsight tools that are available to you. And the two in particular that, if we have time, I'm actually going to walk you through during this tutorial are Nsight Compute and Nsight Systems. Nsight Systems, you can get an idea of what your overall system performance looks like end to end. And then Nsight Compute allows you to do kernel debugging. So you can go through a really nice workflow of like getting total timing with Nsight Systems, figuring out where are your bottlenecks, because it may not be your GPU, it could be that you're IO bound or something else like that, right? And then But if it is your kernel, then go ahead and put it into Insight Compute, debug your kernel, go back to Insight Systems and see how it affects your total system performance. And that little, cycle is a really nice way to be able to debug and get better performance. And we're going to talk a little bit about some of the things that are going to slow down your CUDA programs as we go through this thing. All right. Or maybe I'll talk about them now. All right. All right, so to achieve optimal performance in CUDA, one of the things that we're going to talk a lot about is memory on the GPU. One of the things that makes the GPU so powerful is the fact that we do have basically, a grid of lots and lots of memory, okay? And we're able to compute on each one of those pieces very, very, very fast. And so we have that ability to parallelize on a massive scale on the GPU. And that's what we're looking at, right? So by localizing our memory access, we're not having to move back and forth very much. We're not having to move data across our CPU to GPU through the PCI bus. We're not having to move things from different registers or in different parts of memory. The more localized we can make our memory, the faster it's going to be. And I think that, this is pretty universal, I think, across computers in general, so it should be an easy one to understand. Maximizing the number of active threads per multiprocessor to ensure high utilization of your hardware. It used to be that it was very easy to pick the number of active threads on your processor. It's a little bit harder now, especially with the new architectures that are coming out, but we're going to give you some rules of thumb in order to try and make that a little bit easier. Minimization of conditional branching. The more time that you have, you will have to use some conditional branching. I was in the last time I did this tutorial, someone was like, but I have to put an if statement in here. I'm like, you actually have to sometimes. Like it's not something that you shouldn't do. Just be aware of the fact that the more conditional branching that you have in there, that's going to kind of slow things down. And that's true in a lot of different cases. One of the biggest bottlenecks is truly that moving data between your CPU and GPU across the PCI bus. We are getting to the point now where we are reaching the actual physical limits of what matter can handle, like moving across this piece of wire, right? We're finally getting to that point where like there's not much more that that matter can do for us at this point, right? So transfer rates are always going to be one thing that you have to optimize for. So the more time that you can spend actually doing computation as opposed to moving data, the better performance you're going to get. And we're going to talk about that a lot. And then, of course, the hardware architecture always matters. And then asynchronous transfer features. Unfortunately, we're not going to get into very many discussions about asynchronous transfer features, but there is the opportunity to be able to do computation while you're loading data in at the same time, so that you're constantly moving data and computing at the same time, so it's not serial across every single operation. Okay, and then I mentioned that deployment guide with Rapids that I think is really, really great. I'm going to put this back up at the end, by the way. We're offering a free DLI course that you're welcome to use, but I'll put this up at the end so everyone can look at it. But, all right, from here we'll go ahead and jump into our tutorial. If you want to go ahead and open up your 1.0 GPU, CPU comparison. Actually, before I jump into this, any questions on sort of that lay of the land, the ecosystem of Python? Because I know this can be really complicated with how many different elements are at play there. Yes?
Just a quick question. I don't want to be I'm not a novice, but as the hardware architecture changes over time, does that mean the code is going to have to change as well?
So the question was, as hardware architecture changes over time, does that mean that the code is going to have to change? And I'm going to go ahead and say that the simple answer to that is yes. That older architectures had different paradigms that were used in order to optimize CUDA. So some code that was considered the fastest way to do CUDA in the past is not actually the most optimal way to do it now on newer architecture. So this is why a lot of these libraries are continuing to evolve, because as we move to something like, moving to Blackwell or to, anything in the future, we're going to have better abstractions to kind of keep that implementation detail away. But for sure, people writing kernels or people that are doing, any kind of library development or low-level programming will definitely have to be aware, for sure.
In the future, would it be that a programmer might say, or might program something that says, okay, if you're going to use this hardware, put it in at the front as a code command, and then it optimizes for that? Is that something that might come?
So the question was whether or not programmers would want to put in a check basically for different hardware and then basically operate differently depending on what kind of hardware you're on. I think that a lot of that actually happens under the hood right now. Yeah. So yeah, sometimes you just have to be aware of what kind of hardware you're on. And like I said, as you move through those different layers, more and more of that is abstracted away. So the library developers on, anything on a higher level has already done that optimization under the hood. But if you are working on the lower levels, yes, you'll have to be careful. Okay, so first thing I wanted to do was talk a little bit about, so obviously on your computer, we have our CPU, so our central processing unit, and we have our GPU, our graphical processing unit, right? You almost want to think of these as two separate computers on your machine, right? They don't share any common memory. They run differently. They have different architectures, and they can work in parallel, and they can work together in order to give you good performance. But it is, I think, a really good idea to think of them as being two separate things inside your machine. And that'll keep it a little bit clearer how computation happens on one versus computation happening on the other. But I do want to go ahead and start off with this really cool little Mythbusters movie, just because it's super fun and it'll be stuck in your head for the rest of your lives, to kind of talk about the difference between serially processing something and then using parallel processing.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
when we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target, hopefully. When it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9, 8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
All right, so why do we want to talk about that, right? Because this really does talk about the fact that we are looking at doing computation parallel manner, right? Where our throughput is increasing because we were able to use this architecture in order to do that. So before we kind of get into all this, I just apologize, my screen real estate is not all that great today, but okay, I think that's probably a little bit better. Okay, so we do need to talk a little bit about the architecture of the CPU versus GPU. I'm not going to go into a ton of detail here, but I do think that just really understanding how things are set up kind of helps you understand a little bit better when we talk about moving things through memory, because memory management is such a big part of optimizing our code in CUDA that you can kind of tell the difference. So on the left-hand side, we have our CPU, so our central processing unit. And this one, we're going to take single instructions off the stack, and then we're going to execute them one by one by one. And so you have your core, right? You have your L1 cache and then L2 cache. So the L's, obviously, they go from lower to higher as they get further and further away from the core, right? So L1, L2, L3 moving out from the core. And then you have your control. And so that's how it's moving here. Then what we have over here on the GPU side, though, you can see that we have less of this, control memory. But what we do have is we have a massive amount of space in order to for computation. So this is where we have our data. If we move it from our CPU to our GPU, we're now taking advantage of this huge amount of space that we're able to put memory. And then by operating the same thing on each piece of data over and over and over and over and over again, that's where we're getting the speed up. And so things like, we've talked a little bit about, scientific computing, I think is probably one of the biggest reasons why you would want to do this, right? Where you're taking, for example, like atmospheric data, right? And then you want to be able to compute some sort of filter on it over and over and over and over and over again. You don't necessarily need to be able to do that sequentially. It's the same thing. Let's go ahead and get it in one shot and then move on, right? And so that's what the GPU is particularly good at. And so that's why we would want to do that. I already talked a little bit about the Mythbuster scene. By the way, that video is broken currently in my GitHub repository. I had to find another copy of it because it went private, so I will update that before you guys look at it later today. So, but that's the one. Okay. And so we talked a little bit about how this is almost like having a second computer. And then we're moving things over the PCI. And so when we talk about CUDA, so what CUDA actually stands for is Compute Unified Device Architecture. And I know that sounds like, okay, who cares, right? But what we're really talking about here is that it should be pretty seamless to do computation across your GPU and CPU. That's the idea, is to make this seem like a very seamless experience. Still aspirational, by the way. And so here, let's go ahead and move on to the next one. So how are we doing? Yeah, this is perfect. We'll open up the numba one. Okay, this is not. I apologize. My resolution's a little bit funky, but we're gonna get through this. It'll be fine. So we mentioned numba a little bit, and if you remember in our different layers of abstraction, it was the lowest one on the different things that we were talking about, but still not all the way down into the guts of numba, or in the guts of CUDA. But what's really nice about numba is it does have that ability to compile code down to machine level code, right? And that's where you're getting the speed, is that it's actually a just-in-time compiler. So you do pay a price, by the way, the first time you execute something that's using numba, because it does have to do that compilation step. And you're gonna see that in our examples as we go through this, is that we're gonna have to run them twice, so that the first time you're gonna see how long it takes for that just-in-time compilations to happen, and then after that, you'll be able to see what the speed up is after that. So that is one of the things I did want to mention, though, is that obviously there's always a plus and minus side to using everything. If you're only calling the function once, it's probably, you're paying that overhead tax, may or may not be worth it to you. And so those are the kinds of things to look out for. But what we're doing here is, if you have NumPy-like code, there has coverage over here on the numba side, and then it's going to take that in. It uses the NumPy array and the array interface in order to be able to translate that over into LLVM machine code. Okay? So this is where we're going to start talking a little bit about kernels. So we talked a little bit about the layout of all of our data. We have this giant grid of data that's out there. The kernel you can think of as being like the function that is going to compute on each one of those pieces of data, right? So a kernel is very similar to a function. It's a block of code which is going to take some inputs and it's executed by a processor. The big difference between a function and a kernel is a kernel cannot return anything. It must instead modify memory. So everything that's happening on the GPU is happening within memory or into allocated memory. And then a kernel must specify its thread hierarchy, so threads and blocks, which we haven't talked about a whole lot just yet, but we will just now. So there is a different way of thinking about computation on the GPU here. So you really have to understand what threads and blocks are. And this is what you use in order to instruct your GPU how to process code in parallel. So if you want to think of it as being like on each one of your, okay, I think there's a better, okay. Okay, I'm sorry. So I kind of already mentioned, I kind of doing this backwards, I apologize for that, but the grid of memory that we looked at here, you saw that other picture that had the grid of memory on there. You can think of those as being split up into blocks, okay? So as part of our computation, we have to be able to take that and we're organizing it into the blocks of execution, and that's where everything's going to take place. Within each one of those blocks, we have a certain number of threads that are executing. There is a certain amount of shared memory between each one of these different threads, but in each block you have threads that are also running inside there. So when we look at our overall memory landscape, you can think of it as like we have to kind of, index into our blocks, and we have to index into our threads, and then that's when we get down into our data, right? And those are the kinds of housekeeping type things that we have to keep in mind when we are launching or we're executing any kind of kernel function, okay? Okay. All right. So, what? Okay. Yeah.
This diagram, like if I imagine is what will be the thing that will execute on the board, what will get executed, which threads will execute what like file at the same time.
Right, I didn't really mention warps, so it's kind of talking. So I kind of skipped over that part. Yeah, but yeah, threads are actually they are organized into warps. So kind of like with Fabric, right, where you have threads create fabric and warps from here. Well, it depends on how you orient it, right? I mean, in your mind, in my mind, I have a picture in my head that looks very much like this, right? Where I think of my blocks as being, I guess left to right and moving down, right? Which is, as you'll see in some of our, I know this is a very strange way to look at it, I think, but when you look at some of the way that what we're going to index into, we are going to do some indexing in some of these functions that we talk about. It might be a little bit more, clear there, I think, but you're going to, basically specify which block you're looking at, then you're going to be able to, index into each thread. The warp level, we kind of, we're not really going to have to worry about too much. Right. I'm sorry, that was a very poor explanation. I blame the 3 shots of espresso this morning. But yeah, a lot of this detail way down at the bottom, though, I think that, just being clear about where you are in memory, I think, is important here at the numba level. As you move up in your hierarchy, it's not as important to understand all the bookkeeping on where everything is. And that's one of the nice things about this, right? Like I said, if you are going into a lot of kernel authoring, which, absolutely some people need to move into that direction. You'll have to be very aware of those things as you move up the hierarchy. It's not too bad. But, all right. Okay, so kind of getting back to this, what we're really trying to do here is that we have to be able to specify the number of times we want this kernel to be called. So if we know how many blocks our data is going to take up, we know how many threads per block we have for the data, then we can also give an idea of like how many times are we going to call this kernel, right? So there are two things that we have to look at here. We're going to have to specify the number of threads per block when we're moving into our numba functions that we're going to work with here. They should be a round multiple of the warp size, 32. So just kind of, keep that in mind. A good place to start is 128 to 512. I usually I think most of our examples in here, we're starting at 128 is a good place to go. Like I said, there was a point in time where there was like a linear relationship between the number of threads per block and the architecture. Unfortunately, with the more modern architecture, this is actually broken down a little bit. So you may need to do a little bit of experimenting in order to understand exactly what is the appropriate number of threads per block. But, 128, 256, somewhere in there is a good place to start, especially if you're using anything newer. Yeah?
What's the rate of the number of threads and the performance? Isn't that the more threads you have, the more management needs to be done, and so you're more likely to see a slowdown, or what's the...
Right, so we're trying to hit that speed up between like not having to swap, right? But also being able to saturate our data with, enough threads to do computation, right? So at some point you're gonna see a degradation because you have too many threads that are now all of your computation is going into thread management as opposed to into data management or into computation, right? And so it's kind of like the same way that you would look at like, in a distributed system, right? It's the same sort of problem that you run into. Okay. Yeah.
So, just coming from kind of CPU land, I'm used to having a process that has some number of threads, and those threads can have a shared heap, and they can start working on that heap. And I'm trying to make the analogy here because I will admit, coming from my experience in CPU land, I don't really think about L1 cache, L2 cache, L3 cache. I just sort of write code, try and keep track of what's going to be on the stack and what's on the heap. But otherwise, just sort of write code. In this case, we're writing kernels, and it seems that they have access to shared memory.
Some shared memory.
Yeah, and so I'm kind of wondering, exactly, I guess my questions are is it a kernel per thread, and then they're all sharing some heap, or is there an analogy there that I'm...
It's more along the lines of think of threads are sharing some memory, right? So to your example of the stack or the heap, right? Your threads, the same idea. Threads have some amount of shared memory there, right? And then you have one kernel per thread. So it's one thread of execution.
Okay, and then do all the threads in a block, is that sort of is the block the hierarchy of where the memory is shared, or is it grid shares all the memory, or?
Yeah, that's unfortunately not the best, easiest thing for me to, there are some, so some of our I'm trying to think some of our architectures actually have some different abilities for shared memory and pin memory and all kinds of different memories. So without kind of going into all of the architecture pieces, I think it's probably just best to think of it as you have sort of your L1 cache here, right, as being sort of the shared space for your core, right? think of it as kind of the same thing. And so like if you have all of this different, data that's been loaded into your GPU, into your grid here, and like let's say that, okay, here's your block 1, block 2, block 3, block 4, right? Moving all the way down through here. That's how I think probably a good way to think about it. Does that make sense? Yeah.
Probably seeing code will also.
Yeah, it might be a little bit easier when you see a few examples. It is a complicated memory hierarchy. I just want to, it's not, I'm not trying to trivialize it, but I do want to also point out that like this programming guide is also a really, really good resource to take a look at, by the way. So all of the information here about like benefits of GPUs and like different kinds of architectures and things like that. There's a lot of information in here if you want to get into like the specifics of like memory management and the memory model that I kind of gloss over in this in this tutorial. Yeah. So I highly recommend that. It's actually also going through an overhaul, by the way. The programming guide, we'll have a new version of the programming guide this fall with a bunch of the things that we're putting out, the new education materials. And it will include actually C++ and Python in the programming guide moving forward. So you'll be able to see both side by side to kind of see what the differences are there. So I hate doing that sort of like coming soon, but it is actually pretty cool. Yeah, it's currently in review. We're getting it out there as fast as we can. Okay, so we talked a little bit about okay, so we already went through that, number of times to be called. All right, so let's get to actually running a little bit of code here. So the first one that we have here, let's talk about, we're going to start things off by looking at our CPU and what our CPU function looks like and what kind of timing we're going to take off of this. So let's start with our CPU. We're just doing a really simple list comprehension. For anyone who hasn't used Jupyter Notebooks before, it's just shift return in order to execute that block of code, and that will give us our list comprehension. So we've allocated some memory into data. We have defined our function foo, which is just returning the element, and then we have a nice little list comprehension for foo in I and data. We are going to return that element. So that is our first one. All right. So next thing here, we want to be very, very clear about the fact that when we are launching a kernel function, that we cannot return a value. So here we're going to start bringing in the concept of allocating our output space as well, which is something that you're going to have to do anytime you're running a kernel function, is like creating like your output, or you're doing this like in place in memory or something. But there does have to be a place that you're putting your output. So here we are allocating our data list, and then we have an empty list for our output. And so for each element, we're calling our, if you want to think of this function as our kernel, we're going to append that element onto that list, and that's what we're going to return. So now we have put this into an output array. So we are no longer doing a returning a value. All right, so the next challenge, however, is that we can't have variable or dynamic data structures over on the GPU side. We're going to have to be very, very careful about exactly how much memory we're allocating. We have to do a lot of memory management over on the GPU side. So we do have to allocate the actual output space that we're going to put everything ahead of time. So we have to calculate kind of what that's going to look like. And in this case, all we're doing is we're taking a list from 0 to 9. We're making it a NumPy array, and then we're going to create a NumPy array with the same length as that and just fill it with zeros. Okay? And that is how we're going to move on from there. So, bam, same thing. Oh, I forgot to import, sorry. I just get so excited about it. All right. And so, now that our pure Python function behaves like a kernel, let's use a numba to convert it into one. So From here, let's from numba import CUDA. And so the same thing that we saw before, we have our data. We're going to just create our NumPy array of data, input data. We have our output array allocated, and then we've added this decorator. So the CUDA.jit decorator is what's going to specify that this is the function that needs to be just-in-time compiled into machine code. So the first time it runs through here, right, this is interpreted language. So at runtime, it's going line by line by line by line by line, hits this decorator, and it's like, oh, okay, I'm going to go ahead and I'm going to compile this on the first time it sees it. After that, it's in the lookup. So it wouldn't have to do it again. It's then able to just take the function and execute it next time around. So from here, there are a couple things that I want to mention in here. So first off, the decorator is obviously the most important thing. The second thing that you may notice is that we have this grid in here. And so your grid function here is basically giving you a pointer into that memory space that we were talking about. There are 3 values that can be in this grid. So you're looking at 1-dimensional, 2-dimensional, or 3-dimensional data, basically. In this case, we have 1-dimensional data, so it's telling you basically what dimension you want to index into your data. And that's going to take care of some of the housekeeping on, like, as we move through each one of these pieces without us having to actually, keep incrementing counters and things like that in order for us to index through our data ourselves. And so it's just a convenience function. I highly recommend using it. You're going to see it all over the place in these examples. But all we're doing here is that now we have a way to index through our data, and we also JIT compiled it, and then now we can call it here. And so the same thing that we had before, you can see that we have our foo, 1, and then length data. This is us allocating so we're calling this slightly differently, right? Now at this point we have, we're calling our JIT compiled kernel function, and then we're going to send in our data and our output array, and then we take a look at this. So this one is, okay, so you see these are actually warnings. I did not suppress warnings on this one. If you are like super irritated by warnings, by the way, you can just import warnings, warnings.filter, filter warnings, and then send in ignore. That'll take care of it. But I'm going to leave them in there. This is not going to hurt anything, but there are a few warnings that are going to pop up throughout this tutorial, just so you know. But this one, oh, I lost my place. Okay, this one actually did run on our GPU instead of our CPU. So that, you can see it went a lot faster the second time around. You're going to see me do that a lot. I'm gonna execute it once and then pay that tax on the compilation, run it the second time. That's going to be more like your amortized cost of actually running it when it's on a large amount of data. Okay, so like I said, this ran on our GPU, but let's think a little bit about what happened here. So first off, CUDA.jit decorator. This is what tells numba to compile our code down to CUDA compatible bytecode. And then we did also have to change our kernel inputs to input array and output array. This is because we have to have a reference to both arrays in order to interact with them. And then what about our I? Instead of passing our function the index each time we call it, we can rely on that CUDA.grid function in order to be able to have that indexing. I mentioned that it does just some of the housekeeping for us in the background as far as indexing into our data and keeping track of that for us. There's nothing wrong with doing it yourself, by the way. You can if you want to. But this makes it a little bit easier. All right, and so I kind of glossed over this, but the last thing you notice that we called it differently. So when we were calling it before, we're sending in blocks and threads along with our input and output array. And in order to run this kernel on the GPU in parallel, we need to specify how many times we want it to run. The kernel functions are configured using square brackets and passing the block size and thread size. With our array only being 10 elements long, we specify a block size of 1 and a thread size of 10 which means that our kernel is running 10 times. Does that make sense? So it's moving only in one dimension across all 10 elements. And you saw that if you look at this warning that actually came out of here, yeah.
So, would a thread sometimes be executed more than once if you had a large array and you couldn't have as many threads as elements in the array? But it's just that now we only have a small array, so you can do each thread will only run once.
I think that, so I'm not quite understanding the question.
Mapping between the number of threads and the number of like elements in the array.
Not always, right? I mean, that is not something that we would be able to maintain across everything. This is just a very small one, like you said. Yeah, I think I get what you're saying. So in this case, like, coming up with the number of threads and blocks, you're actually gonna get some practice with this, by the way. But I did want to point out here the warning that came up here. You can see that this, like, the warning that actually came up was that you might get a GPU underutilization for low occupancy. This is a good warning for it to come out because, yeah, like running 10 elements on your GPU is probably not the best way to get great performance out of your GPU, right? And so, but it's great for demonstration purpose here. But let's look at something that's a little bit bigger. Now that we've run this one, let's take 30 million elements and see what happens there. So we'll create a array of random elements that's 30 million elements long. And then we're going to create our output array. And then we're going to go ahead and create this little, use the magic function. I don't know how familiar you are with Jupyter Notebooks, but anything that has a % sign in front of it is a magic function that's part of Jupyter. And so we're going to use the timing function. And this is just going to, basically for this block, it's going to take a timing for us. And all we're doing here is we have our function foo. We're going to take every element in our random array, we're going to multiply it by 2, and then we're going to put it into our output array. Okay? In NumPy, obviously, we would do this with broadcasting. You wouldn't want to do this. Right? But I always feel the need to say that. All right, so 8 seconds. Let's see, yeah, roughly around 10 seconds. This is on our CPU, so this is with our sequential operations, okay? Next, let's take a look at the CUDA kernel. We're gonna import math for this one. We're also gonna use our timing function. We have our random array where we're gonna create our NumPy array with zeros. We're specifying the number of threads as 128. Remember we mentioned that that's kind of a rule of thumb, 128 to 56, somewhere in there is a good place to start as far as your number of threads. And so this is where it gets into kind of talking about that memory model a little bit more. So, you know, your threads are going to be inside of a block. So in order to understand how many blocks we have to specify, we take the amount of data that we have, and we're gonna divide it by our number of threads and take the ceiling. So in this case, we're taking the ceiling in this one because we want, like, we'll probably have a little bit of extra data that doesn't fit neatly into the number of blocks that we have, but we have to make sure that we have enough space in there, right? And the thing is that, like, once you do something like that, you do have a little bit of extra space allocated in your block, right? And we have to be careful that we don't run out of our data. If we have memory out of bounds, this is going to errors. Those are going to start becoming kind of, they don't have a predictable behavior at that point. You could end up with strange values. You could end up having some sort of runtime error that pops up. There are a lot of different things that can happen. So we do have to be very careful about how we're indexing across this. But we have to have the number of blocks necessary to fit our data in it, even if it doesn't fit 100%, you know, evenly. Okay, and so here, this is a much more meaningful example, right, where we have the number of blocks that we're setting in, and we're setting in the number of threads. here, and then we're going to send in our random array and our output array and have this execute. All right. All right.
I have a question.
Yes.
So if you run this and somehow misselects threads or whatever, depending on who wrote the code and how they wrote it to use it, and I'm using it at high level Python, will it just choke? Will it tell me you can't do it? Or is it the coder that's going to help me with that, whatever they wrote? I don't understand.
Right.
Does it tell me something?
So the question was, basically if you have an index out of bounds error, what's going to happen and who handles that and who's going to catch it? And I'm just going to go ahead and punt on this, say that it depends, which is my favorite answer to everything. Depending on how the code was written, if it's catching the errors and handling them in some sort of graceful fashion, that is kind of, depending on which library you're in, the lower you are on the stack, the more of a problem this is going to be for you to figure out. And so at that point, I would say that this is kind of what I was getting into, is that sometimes you may even get into a situation where it doesn't throw an error, it just gives you a weird answer. Because you, yeah. It depends. It truly depends. Yeah, and I know that's not a comforting answer, but it kind of, yeah, there are a couple, I can actually think off the top of my head of a couple of different examples that could go either way. I know that I myself, building curriculum and example problems and things like that, I feel like I run into a lot of different errors. Especially with some of our newer libraries that are coming out. And yeah, sometimes it's very clear to me what's going on, and other times it's a little harder for me to decipher what actually happened.
Okay,
so, yeah.
I have a Python code that I wrote, which is going to be remedial. Can I put in a stop, say, if this goes too long, shut down, give me back the computer?
Yeah, you absolutely can.
All right, then
yeah. That should, yeah. Yeah, very defensive programming. Yeah.
So when you do this calculation of the blocks, basically you're just specifying, your data has some shape, some size, and you're specifying the number of those threads. Is there a reason that we have to tell the kernel or the CUDA JIT the blocks and the threads? Is there a reason that it doesn't just compute the number of blocks based on your data and the number of threads you want to use?
Yeah, a lot of people have actually, Keith, do you want to answer? Yeah, this comes up every single time.
There actually is an API where instead of basically manually specifying the blocks and threads, you can call foo.forAll and pass in that array, and then it calls an API under the hood to basically try to calculate the optimal way to structure the program based on it. That being said, because we're in Python land, the shapes of these arrays are all runtime as opposed to necessarily compile time. And so you don't always want to necessarily launch with that configuration. But yes, there is built-in API to basically just automatically handle it for you to just pass in the
And a lot of it also is just, to reemphasize, this is for also demonstration purposes so that you can understand a little bit better what the memory model and the programming model is doing. Right, because as I mentioned, all of these concepts are universal, right? So being able to apply this to writing kernels in some other, some other way, using some other library or something like that, the concepts are universal. You're going to run into these concepts over and over and over again. Okay.
You mentioned earlier with the CUDA-enabled function, it could be, I think, 1, 2, or 3-dimensional.
Mm-hmm.
Is it hard capped at 3D? Like, what would you, if you were to
Yeah, I recommend actually reading the documentation on that one. Maybe we're about to take a break. I would definitely open that one up. It's but the short answer, yes. But it is a fascinating function, actually, and this is also another one of those questions that comes up every tutorial, is that like what exactly it's doing under the hood. I mean, the short answer is that it's giving you a pointer into your data. The longer answer is a lot of implementation detail depending on the shape of your data. Yeah. All right. So now we've gone to a few hundred milliseconds based on what we're doing here. Let's see how much more we have in here. Okay. We're going to take a break as soon as we finish these. All right. So, okay. I'm just remembering where we are. Okay, so, all right, so for this example, NumPy is still going to be faster than our GPU, by the way. And why is that? It's because of broadcasting, right? NumPy is incredibly well optimized for this type thing. So determining where that barrier is, by the way, where you start getting the really great performance out of your GPU versus your CPU is one of those things that also kind of depends on your data. But, you know, massive amounts of data that doesn't fit in memory, for sure, you're going to get a better, I actually can't say for sure, but you're probably going to get a huge speed up. But, you know, NumPy is quite well optimized in this area. But the reason that this happens is because of our memory management. So we're going to talk a little bit about moving things back and forth between the CPU and GPU. You know what, actually, I am going to go ahead and pause here for our first break. So let's try to come back in 13 minutes at 9:30, and we'll pick it up from here. And we'll go into the memory management piece here. All right, thanks. Yeah, so that's...
There's another hierarchy there once you get to in addition to red orbs, clusters.
Yeah, and I've seen Jones told me this at like
Your data size is larger than your memory combined. How does it integrate with that? actually is the problem with these bigger blocks.
Yeah.
You know, like, so.
Are you saying-
examples, we're loading all the stuff and then executing it all. What is the stuff? Exceeds the boundary.
You need to, at this level, you need to restructure your algorithm.
level, you need to process it only as much as you can fit in there.
Yeah, so you need to basically create a streaming algorithm at that point, and like, at that level, if you can, use one of our higher level libraries that can handle that. Because like, it is not trivial, because then to get it to perform it, you also need to do tricks. And I don't know if we're gonna even cover in this tutorial about like, you know, okay, just like compute on like one batch of data while transferring, you know, other batches of data, and like maximize all like.
That's 301.
Yep.
Once that happens, this is gonna be more like a long.
Well, I think that was the spirit of this question was if the data is too big, do the threads execute twice? And the answer is yes, but you have to unload and reload the data to operate.
So I wasn't sure if it was about data being larger than GPU memory, or if like.
That's what I understood.
A GPU has, say, like 1 million threads, like 1 million hardware threads availability, and it's running on 10 million elements, basically way down under the covers, and the driver schedules that work and figures out, like, okay, you know, as I chew through this work, I'm going to be scheduling multiple things. Like, it's going to.
Basically, it's doing, you have to do that at a higher level of loading.
Well, so if it fits in GPU memory, you can schedule more work. The driver will actually just happily schedule that on the code. It's just like, you know, if I have 16 gigabytes of GPU memory, I have 100 gigabytes, right? I can't just shove that, like, you can use, there is something called managed memory, which allows you to basically just use host memory transparently as a GPU memory.
Obviously,
Yeah, but and then it, like, it basically changes things in and out. We're not going to cover that in this tutorial, but there's an option for like when you're starting to deal with larger GPU memory, there's lots of performance when it comes to that. Like, there needs to be very mindful of how you do your work and structure your algorithm and transfer your data and everything.
At the same time, we're also trying to turn our laptop into a computer.
Maybe you are.
But, you know, but if I have a desktop with some graphics card in it,
Yep.
that's what I'm, $20,000 desktop.
Even your, you know, laptops under $2,000, the GPUs that you can get in them nowadays, the things that you can do with it, is wild. Sure. I would be good. Yes, that is more or less abstracts that way, and we don't cover it in the tutorial, but all of that concept is exposed as well. Where if you would rather explicitly like have, you know, threaded out objects, block layouts, and stuff like that, there's APIs to explicitly change this. Yeah. Yes, so I don't think anyone here, we have a whole team that's basically pushing on the next everything there. And
Mainly when they asked the question about determining algorithms that still go next to their one out.
I mean, partly, we support computer systems, ecosystem. For a lot of these libraries, it's the Riehl nexus that has some implemented just because CUDA, like, underneath numba CUDA supports 2 major CUDA versions, and it does that in pure Python, so it doesn't need to be separate packaged for CUDA version. And same thing with the core. It'll be more. We don't. Yeah. More and more Python packages are moving to a place where they just transparently handle the full CUDA versions without any separate packages. And we're generally going to keep pushing as hard in that direction as we can.
user experience. Yeah. Like at a certain point, there is just like, there's different binaries there, you have like 8 separate packages. The second that you have like 12 or 13 packages, it just carries forever. So I think like the biggest target is you really hope to make high twitch better experience, bit variance.
Yeah. Right now, Amazon, I don't know if I'm anyway.
Joe's not at
So I would, I'm not going to design
Yeah, like,
okay, cool. I support everyone that does all this stuff. And, yeah, that goes so that. Right now, because, but none of them don't have tile 6 and Moonskis. We have packages that have torch in addition to these. Yeah, and it becomes impossible to package those things. Yeah, I have a giant. We, so recently, acquired the to get it right. Didn't say it's not right. There's a little available. Bits are Linux architecture.
Did you meet Andy Terrell?
I was not actually in the start. The other 2 people on my team that does my team.
Okay. Andy Terrell will be at SciPy. You should try to connect with him. Yeah. Like his team has been driving, like his team has been collaborating with different engineering teams and they focused on packaging.
Well, I'm taking the tutorial tomorrow. Right here.
yes.
Oh, there.
Yeah. So what was but actually, don't use that.
Finding out later on packages.
So I didn't use those. I mean, I watched it.
So it was
Yes.
Specific use case.
But somehow,
So I wonder how to
that was a same I picked up Rust just
so
like there's something nice about having Tyler just scream at you instead of finding out what really happened.
I don't think anybody really just we would see the trend that
now I do like crowd capture / control. We're sort of like a running It's usually profiling. We're not going to so we'll just grab right out of
you should his name is Andy Terrell.
so basically Alpha has the sound.
Driving it's weird. It's a product that
We're gathering data so that so it's trying to understand like the tidal power, whereas the wave power actually generates energy. So one of the best things we can plow or sensing when the deer sensing when it's actually happening.
All right. we are at 9:30, so we'll go ahead. We have a lot to cover, so we're just going to keep going. All right, so we talked a little bit about so we saw a big speed up when we went over to the GPU, which is great, but not as much of a speed up as we would have liked to. And this is kind of going to get into the memory management piece of this. Since we are talking about a CPU and a GPU, these are effectively two separate computers, and each one of them has their own memory, which is what we're really managing when we're moving between the two. All the data that we worked with so far, we created in NumPy, and that's over on the CPU. So in order for numba to work with this data on the GPU, it's been quietly copying that data over to the GPU, and then that's where it's going to execute. So one of the things that we can do here is to explicitly move our arrays to the GPU ahead of time with CUDA-enabled So this is where we're going to start talking a little bit about how to move your data back and forth. There's a great question that popped up that apparently I did not really totally understand the question that you had asked earlier. And so we had talked a little bit about how if you don't have your data fitting, precisely inside your blocks, and you have, extra threads, or you have threads per block and things like that, are they, how does this affect your performance, right? And so if you don't, in this kind of paradigm what we're talking about right here, we are specifying the number of times that we're executing our kernel. And so we would have to change our block size, change the number of threads in order to make our data fit this paradigm right now. However, in something that is much, much larger, we do start getting into the situation where we may in the background be moving data in and out of our GPU in order to get better performance. So, because we can't, obviously, we have a lot of data, we have a lot of memory, but we don't have infinite amounts, right? So none of that is happening in this kind of situation where we are here at this level. Everything we're going to have to specify ourselves, okay? And so that's what we're going to do here, is where you kind of start to see what this looks like. So next piece that we're going to do here, we're going to create a GPU random array. So here we're calling CUDA.toDevice and sending over the random array. Our GPU output, we're going to do a CUDA.toDevice, and we're sending over that zero-filled NumPy array. Okay, so let's go ahead and execute that. You can see here that when we look at our GPU random array, now we do have a device array. So the device ND array is what you're seeing here, as opposed to a NumPy array, what we had before. And by doing it this way, we are going to, basically save that copy is what we're doing. But also, I do want to point out that this is one of the first places that you start seeing the effects of having this common ND array API expressed on multiple levels inside the CUDA stack. And so all of those different frameworks and pieces that I talked about, there is a lot of interoperability between them. And one of the ways that we're able to do that is with common APIs and common interfaces. And the array interface is probably the most important one. And so being able to move between NumPy arrays and device arrays and even into tensors and things like that, we are able to move seamlessly between these by having the same interface implemented at different levels, okay? So this is where you're kind of starting to see the beginnings of that. And here, we'll go ahead and we're going to run this again. And we're going to run it on the, let's see, we're going to run it 100 times here. So the -n 100, we're going to run it 100 times. We're specifying our number of blocks and threads. And then we're sending in our, we have our device arrays for both input and output. And you should see quite a speed up, right? So now we've gone down into microseconds because we have no longer doing that copy. So you can kind of see how that performance hit, I keep harping on that, like the less time you spend moving data across that PCI bus, the better your performance is going to be. The more you can handle your memory, the better your performance is going to be. What's your question?
Just initialize the array, you don't need to be able to use arrays
You can actually, you can specify it over on the GPU itself. But what we're doing here, in this case, we do have the random array that we allocated in NumPy. We're sending that over, and we are copying it ahead of time, if you want to think of it that way, right? So by moving that out of the equation, that's how we're able to just focus on that kernel execution now that we have data over there. Okay.
I think there's going to be a later on that shows kind of how to do common array APIs on CuPy, and then it all makes sense as far as.
Yeah, it is a, but, yeah, I think that most of the things that people ask about are things that our wonderful engineers have thought of too. So there's always a way. That's what I'll always put it. There is always a way. All right. So now that we have executed this, let's move it back out to our host. So now we're gonna pull it back out, and now we're back into a NumPy array again. So this is out on our CPU. Okay. So we allocated in NumPy, copied over to GPU, executed on GPU, and then copied result back out over, okay?
A quick question. I'm not even sure if it's relevant, but I was under the assumption that using rebar, a resizable bar, would kind of bridge the gap between CPU and GPU, if that makes sense.
I'm sorry, a resizable rebar.
That is used for the Intel GPUs, where you can use your GPU's memory. It's more accessible for the CPU.
So
yeah.
Make it easier from a programming standpoint, in that like your memory basically be able to transparently access the memory, but you're still up against, you only have a certain limited amount of bandwidth on your PCIe bus to move between CPU and GPU. In the gaming world, that's not as much of a problem, simply because you're only transferring very small amounts of data and you're just doing all of your rendering from GPU. In computation land, if I'm moving a gigabyte of data between my host memory and GPU memory, that PCI Express must very quickly becomes a problem.
So there would be no like outside of using that for like deep learning or anything like that. There would be like no outside to use that for any deep learning or anything like that.
It would make it would, if you were building really low-level software that like, you know, were more trying to more explicitly manage memory yourself, it might make it easier to like programmatically access things, but you're using kind of the existing APIs that we give you across various libraries, it's not being that relevant, and it's not going to really change anything.
All right, thank you. I hadn't heard that one before. Okay. All right. So both of the data movement operations, they take time. But the computation that we're executing here is trivial. As the calculation of our kernel gets more complex, the percentage of time spent copying data becomes smaller and smaller and smaller, right? So memory management is useful in other places too. We may wish to write code where we write many kernels and chain them together. It would be inefficient to copy the data to the GPU and back again for each kernel call. And this is something that happens quite a bit. You'll see, hopefully if we do have time, you can look at this actually in our Nsight compute portion of this tutorial, where you can see a kernel execution and then a gap and then kernel execution, things like that. And what's happening is that you're actually, basically CPU to GPU for execution, you're moving something back to GPU, back to CPU, back to GPU. Instead, you'd really like to just move your data once, execute all your kernels on it, move your data back once, right? And then that way that you're getting a lot more performance out of it. And because those copies are expensive and you have to pay that tax every single time.
Are kernels all pre-computed, or do you have to compute it? How long does it take to compute and move kernels?
So in this case, we're talking about within numba land. What we're doing is we're writing the kernel, and then there's the one-time cost of just-in-time compiling it, right? At that point, it's available for lookup, so it's able to load that in and execute it. Does that make sense? So there is a tax the first time that it comes across that. But then after that, that's where you're able to amortize that cost. across all your data. Oh, are you talking about invocation? Oh.
Well, I'm saying if you have 10 kernels you want to execute on your data, how does the core on the GPU access those kernels? Does it take time to reprogram the core in the GPU to execute those different computers? Does that make sense?
Oh, no, it's a very low overhead for the kernel launch, very low. Yeah, and so you can, actually one of the things that, nvmath-python, Sergey may be even kind of alluding to, is that it has the ability to do things like kernel fusion, right, where you're able to take multiple kernels and actually fuse them together into one kernel. And so you can even get rid of that kind of invocation cost. So, yeah. There are a lot of really cool things you can do in CUDA. Just hopefully we'll get there. All right, so let's walk through this example here. So memory management, blah, blah, blah. Let's go to first thing we're going to do here is we're going to move our array to the GPU. So here we're calling to foo, sending over our blocks and threads, sending over data and output, and then we're going to move data back to the CPU. Then we're going to move it again to move data over to the GPU when we call bar. So once again calling over same number of blocks, same number of threads, or data and output, and then we're going to move back to the CPU. We moved our array to the GPU the third time when we call baz here. And this is what I was talking about where you have like that, data moves over, execution, move back to CPU. CPU call, back over to GPU, back over here. Each and every single time you move back and forth, you're losing some performance. You're spending less time utilizing your GPU. Okay, so how do we make this better? This case, what we would want to do is by using that call that we learned earlier today, we're going to move the array over to the GPU once. So now we've moved everything over to the GPU. We're going to move our output space over to the GPU, and then we're just going to call them in succession. So we're going foo, bar, baz right after each other, and then moving everything back over to the host. Okay? And that is going to be much, much faster. Okay? And I don't think this one is actually, no, it's not executable, but basically this is the kind of practice that you'd want to do, right? So by batching up your computation and batching up sort of your data movement and memory management, you should be able to also reduce some of those bottlenecks. Okay? All right, now it is your turn. Let's open 2.1, and this is the numba lab, okay? So, how many people have done FizzBuzz before? All right, fantastic. For the rest of you, this is going to be a lot of fun. I'm just going to pull up the rules for this one because, hang on, FizzBuzz. All right. What you're going to do is you're going to code FizzBuzz here. And so what you're going to do is if it's divisible by 3, you print fizz. If it's divisible by 5, you are going to print buzz. If it's divisible by 3 and 5, you print FizzBuzz. And if there is no, if it is not any of those conditions, then you just don't put anything out here. All right. And those are the rules of the game. It's actually an old game where I was supposed to teach kids how to do division, but you're going to try this over here on the GPU. And so I think we have you going from 1 to 50 million as you run through your array, and check to see if it's divisible by 3, check to see if it's divisible by 5, put out your answers, and then give it a shot. We'll, let's take about 15 minutes to work on this one. If you have any problems, raise your hands. We have our wonderful TAs in the back, or myself. We can come over and help you, and we'll walk through it all together when we're done. Just one thing I was going to mention, if you come down here and there's a suggestion of using values 1, 2, and 3 to represent fizz, buzz, and fizz buzz, I highly recommend doing that. Strings on the GPU is a bit of a tricky little thing. And if anyone's familiar with cuDF, it actually uses a library called cuString underneath it to be able to make strings more friendly on the GPU. But you may run into some issues if you do not use 1, 2, and 3. It'll be a lot better to do that. How's everyone doing? Need a few more minutes? Anyone need more time? Are you ready to move on to the answer? I'm having trouble reading this room. Yes, move on? All right, cool. We're going to move on. All right, so all the answers are in the next notebook. Let's go ahead and just walk through this. So first, our imports. We're creating our from 0 to 49,999,999 NumPy array. And then we are going to create our output array. So now this is where we calculate that block size. So we're specifying 128 threads. Remember, it has to be some sort of multiple of 32. So rule of thumb, good place to start. Importing math, just so that we can get that ceiling function. And taking the shape of our data, so in this case, since we do only have one dimension in our array, we're taking that length of the data, and then we're dividing it by the number of threads that we specified, and taking the ceiling so that we have just a little bit of extra space in our last block to accommodate all of our data. Okay?
So does it matter that the block is not an integer? Specifically cast it as an integer. I just did a print statement so I could see how many blocks it was, and I noticed that it's a float, even though ceiling should be an integer.
It'll be fine. Yeah, it shouldn't be like a fraction or anything like the kind of, but it'll do that casting itself. It'll be fine. But especially, that really does come out as a float.
I use NumPy seal since I already had NumPy.
Okay. I'm curious now.
So I just printed the two full threads blocks just to see Kind of like above where it says output equals output.
Yeah.
I just, right below blocks, I just put a tuple of threads, comma blocks, and just to see the output.
Okay, well,
It did error with flow.
okay.
Yeah, but it was a very useful error. It said flows can't be a flow.
Right. I was like, it can't, it has to be, you're right, it has to be an integer. It has to be, you know.
Maybe math does.
Yeah, I think it does. We have disabled all of the, you know, helpful functions in Jupyter here because it's a tutorial, so we can't quickly look it up. But yeah, I'm sure it's an integer. All right, and so here's the meat of our function here. So we're going to define fizzbuzz. We have our input array, our output array. We have our pointer basically is going into the grid. So that's what's doing our accounting for us as we move from block to block to block. And then we have our input array. This is how we are able to match up basically where we are, doing that indexing into our input array and then making sure that we're pulling it into the right spot in our output array. Okay, so those are the ones that they match up with each other. Okay, it's just an index. And so first check, is this divisible by 3? If it is, then let's go ahead and put 1 in there. Okay, if this is divisible by 5, let's go ahead and put a 2 in there. So then that's where we get fizzbuzz. And if it's divisible by 15, then we put in 3. Okay. And you'll probably notice, right, that here, this is a question that came up before because somebody was talking about that, like, if it is divisible by 3 and 5, that you're actually overwriting your answer twice before you actually put that 3 in there. That's fine. Okay, because you're still getting the right answer. All right, so let's go ahead and define our function. And here we're going to run it. So we've already specified the number of blocks, the number of threads we're sending in our data. We have our output array. And then let's take a time on this one. I'm going to run it a second time. So you can see that we ran in 144 milliseconds. And our output array looks like this, right? So exactly as you would expect it to look. So 1, 2, 3 is divisible by 3. 4, 5 is divisible by 5, 6 is divisible by 3, and just kind of all the way through, right? Okay, and so for an extra credit problem, this is just a little bit of a indexing problem. So what we're going to do is we're going to look for the highest instance of fizz. So we're going to use the numpy where function here. So it takes a conditional. So anywhere that we have an output that is equal to 1, so we know that that's our fizz answer, we're going to take that and it's going to tell us, give us a binary array of everywhere that is true, right? So it's giving us all of those. And then we're going to go ahead and we're going to, we're pulling off basically the last index. And then so that index we can use to index into our data. And bam, there you are. That is your last, that is the highest one. So it's really just a question of what is the highest instance of fizz. We're going to, which is divisible by 3. So once again, using our where function, we're looking to see everywhere that it's equal to 1. So everywhere that's equal to fizz. And then we're going to go ahead and that is returning a 2-dimensional. So we pull the first dimension and then we pull the last index off of it is what we're doing here. Okay. All right. Okay, at this point, I'm going to ask y'all to do just a little bit of cleanup because we're going to run out of memory real fast. Unfortunately, we can't give you infinitely huge GPUs for this tutorial. So if you don't mind, come over to kernel. And we're going to shut down all kernels over here. Go ahead and shut all of them down. And that's going to free up our memory. You can go ahead and close these old notebooks. And then we can start fresh with 3.0. Okay. Otherwise, on this notebook, you're going to run into an out-of-memory error. So just a good idea to just do a little bit of housekeeping before we get in there. Oops. There we go. Okay, so this next one, let's try something that's just a little bit more complex. And the first ones that we were working with was all one-dimensional data. We were only working with arrays of, basically floating point numbers. And this one, let's talk about a Gaussian blur. So we're going to use image data, so we're definitely going to be working in 2 dimensions and higher dimensions, in fact, because we have color and saturation and all of those, it's more complex data type than what we've been working with before, but still numerical. So in this case, let's go ahead and pull in matplotlib, numba, numpy, and math. Okay, and so you should be able to pull in the numba logo. And this is what the numba logo looks like. This is, in fact, trademarked by NumFocus, so believe it or not. All right, let's move the image to the GPU, and then we're also going to create the output array that's going to have the blurred version of this image in it. So in this case, exactly what we did before, we're going to take the image and we're going to move it over to the device. Okay, so that's going to do the copy of all of our information over to the GPU, and then we're going to create the output space as well. So same shape as the image that we sent over there, and we're going to allocate that as well. So same thing we did before, just now we're using multiple dimensions instead of just one. Okay, this is where our grid function is really going to help us out a lot, by the way. So before we write the blur function, we need to talk about the multidimensional indexing. Before we always had, the CUDA grid 1 to get our I value, and that 1 in the call refers to the number of dimensions this index should have. We are working with a one-dimensional array, so it made sense to have a one-dimensional index, and that was what was happening in our grid. Okay. Now that we are moving to 3 dimensions, 2 for X, and 1 for channel, right? So this is our red, blue, green plus our alpha data. We're going to have to move into 3 dimensions, right? So our grid is going to be grid 3. Make sense? And this is what's going to give you that pointer into all 3 dimensions of your data. Okay, it'll make a lot more sense when you see it in action. Yeah. Yes, it should. Good call. If you wanted to open a pull request on that, that would be pretty awesome. All right. So we have a 116 by 434 by 4. Those are the dimensions of the data that we're sending over, right? So the last one is that red, green, blue alpha. Then we have the pixels in each one of our image, right? So 116 by 434. That's what we're looking at. Okay, so we want our CUDA kernel to operate on every single pixel in this image. We could continue to use I and ensure I is 116 by 434 by 4 and unwrap our indexes ourselves to isolate each one of these pixels. But instead, we can use those 3-dimensional indexing provided by grid. Instead of I, we have X, and then we have Y, and then we have channel indices. So we've now split them into 3 using that convenience function. Okay? First off, we need to specify the 3-dimensional thread block size, and let's continue to use the thread size of 128 for this one. But we can specify this as 3 numbers which multiply to be 128 as well. So if we have threads per block equal to 128, we can also, like it's saying that we can actually split this out. As long as it equals 128, we're okay. And I know that's really, really complicated, but this is why all of those really nice little grid indices are so helpful so that you can keep track of like exactly where you are in your data. All right. So here, next we need to calculate our block size. We're going to use the dimensions of our image to calculate how many threads we would need to cover our image. So in this case, we're going to do our blocks per grid in the X direction, Y direction, and Z direction in each one of these. So we're going to go by each one of those dimensions, and we're going to divide it by the threads per block for each one. Okay? So we're not using 128 total for every one. It is getting split across in 3 different dimensions. We're specifying how many threads per block in each one of those dimensions. We're using that to specify how many blocks per grid in each dimension. So we have to split it up for each one. Okay. And the last one, this is greatly simplified because we only had 1 dimension. All right. So that's what we've got here. So blocks per grid, you can see here we have 58, 28, and 1. Not really too surprising right here. All right, if we multiply our threads and blocks together, we can see that we have a grid that is slightly larger than our image. Okay? And it's the same thing that we saw before. When we're using those ceiling functions, we do have to have an integer, as we were discussing over here. So there's usually a little bit of extra space in there because we do have to have enough space to put all of our data in there. Okay? So the next thing, writing our blur kernel. This is a little bit more complicated than what we've done before. As you can see, our kernel needs to take in the image and the output array. We need to get the grid position to operate and then perform the blur on the image in that position. We only care about blurring across X and Y dimension, not across your color channels. So we're just going to pass the C value along. So remember, we have a X, and we have a Y, and we have a channel. So channel C, we're not going to care about that one. We don't need to blur on the channel. We're only going to use X and Y. Okay? So here, let's walk through this real quick, or as best we can. Let's see if I can get a little bit more screen real estate here. Apparently not. Okay. All right, so our CUDA.jit decorator here, we're going to define blur. This is our input and then our output arrays. And then with our 3-dimensional grid, we get the index positions in each of the 3 different directions. So X, Y, and channel, we're using the CUDA.grid. And we specified 3, so that is for the 3 dimensions that we're working in. Because our grid is slightly larger than our image, we do have to look for out-of-bounds errors on this one. It's generally a good idea to put in checks for out-of-bounds errors when you're writing kernels, by the way. And I know I mentioned that you try to stay away from conditional branching a lot if you're using numba and or you're writing kernels, but this is necessary, right? Especially if you're working on anything that is going to take any of the values around it in order to calculate a value. It's really important that you don't get into some sort of undefined behavior by pulling in data that hasn't been allocated or something like that, right?
Well, also really common in image processing that you have to stay away from the edges, right?
Yes.
You don't want to index past the edge of the image.
Right.
So where is that check to not process, for example, 0, 0, and then subtract 1 from X and Y?
Yeah, we gloss over that in this one. Yeah. Yeah. No, it's a very good point. The comment, I keep forgetting to repeat this for the recording, but the comment was that in image processing, you also want to be careful of your edges because you don't want to pull in anything that's outside of your image. And so, for example, checking for 0, 0, if you look at this, you can tell that we are in fact not doing that. And you'll actually see that in the image when we look at it. All right, so we're going to look at the edges of where we are at. Excuse me?
Is X plus 1 going to throw the out of range error because X is still less than I am
Wait, what?
So we still use x, so we check for x less than average, because when there is x plus 1 by.
Correct, right. And so this is where it does, in this case, right, we are using a blur function, right? So we are looking at the pixels around it, right? That means that we are going to go outside of our image range. And maybe this is a good point to make, is that those checks are ours, right? We specified that explicitly, that these are the checks that we're looking for. There's not going to be anything that errors out if we move outside of our ranges, right? So if we didn't have any of those checks in there and we just started going all over the place and just, you know, walking all through memory and stuff like that, even if it's not allocated, nothing's going to stop us. This is why it's so important when you are getting down into this level, you know, all these checks and all of the, you know, convenience functions and indexing and, you know, memory out of bounds errors and things like that. The higher level libraries definitely handle a lot of that for you. Yeah, but no, nothing's going to stop you from doing it. And like I said, when you look at this image, I'll show you, when you run it, you'll see that hard edge on the side because, you know, getting it started basically. All right, and so what we're doing here, we're looking at, once again, C is only being passed through. So for each one of our pixels, we're looking at the pixels all the way around it. And then we're going to basically add that all together and average them. And that's going to create our blur. Okay. All right, so now running our kernel. Okay. I was just like, why are we running this 5 times? Okay, now let's run our kernel a number of times to get our desired level of blur. So we're going to run it 5 times, and each pass you're going to start getting, it gets a little bit more blurred than the last one. We also need to need our output to become our input. So in this way you're also going to be swapping. So your output becomes your new input into the next round as it comes through. And so as we run it, you'll see that as well. And then at the end, we're going to take everything, all of this is happening over on our GPU, remember? And so from there, we're going to copy it back over to our host, and we'll be able to take a look at it. Okay. And now let's pull it back over and look at that nice little blur on there. You can tell, by the way, exactly what you were talking about. See this little gray edge here? This is exactly what you were talking about going outside of the image. I have no idea what value it pulled in when it did that, but you can see it in the image. Okay. All right, so let's move on to our next numba lab. Go ahead and open 3.1. And this one is going to be your chance to work with the same figure, and we're going to work on turning it into a black and white image. And this one, 10, 15 minutes. I'll check back in around 11, 12 minutes.
Which one?
Yeah, 3 is another. Yeah.
city.
He seems quiet, so I'm just going to say hi.
Yeah, absolutely. We're just doing your tutorial.
That's fine.
Yeah.
It's good. How's it going?
It's going very well, yeah. So we had no problems getting into the DLI this time.
Good, cool.
Everyone got in, and it was like, it only took 10 minutes for the whole class to get up and working. So I think they have addressed some of the issues we were seeing.
That's good.
Yeah. Cool. Yeah, I was talking to Keith, and it was like, I wasn't able to get any of the CuPy stuff that I was running in this tutorial, and he was like, yeah, I know. And I was like, okay, I just needed you to say that, because Andy keeps asking me, and I'm like, shit doesn't work yet. I keep wanting to show people all the like CuTile demonstration stuff.
Yeah.
Just not right.
I feel like Bryce shows stuff and it looks really cool. It's like, oh, try it. But I know it's like, Bryce like makes it work.
Right. That's what, I mean, exactly what we talked about. The hope is to turn like a 4-hour CUDA Python, low level, kernel authoring, CUDA core, CuTile, blah, 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 whatever. Low level tutorial, 4-hour rapids tutorial, right? And then if we need an 8-hour course, we can do both back to back. And then that's what we'll have for the Python side for DLI as well.
Great. Cool.
Yeah.
I didn't want to come and just watch you do this tutorial because I thought that might be a bit
pressure. I don't care.
Like,
It's all good. I'm just like floating along with life these days. How's the jet lag treating you?
it's okay. I mean, it's what, 6:30 in the evening, so this is good. It'll be later that I won't be okay.
Crashed.
Yeah. No, it wasn't too bad because I arrived in the afternoon yesterday, so it's like I could stay up into the evening and then I could sleep. And it'll be going home, it'll be hard. But,
Paris was hard after we left y'all in London. Like they had us scheduled like every minute of every day. I was so busy. I was run ragged. I barely saw anything in Paris at all because I was just exhausted.
yeah, that was tough.
But the Python tutorial, we did 2-hour Python tutorial with no registration, and we were completely like standing only. Like it was one of the best attended ones. It is.
Okay, so each of us
I'm just
going how about 25?
Yeah, I think I went ahead and reserved 50 hot labs just in case, but yeah, I think you're right, like 25. We have another one left. Yeah. But
I was wondering, like, they have an
so that ML one was at the same time as this one. And I went ahead and volunteered in the TA on the cuDF one tomorrow because I'm so curious to see what they're doing.
I know where they're going.
Oh, is it really? Okay.
It's a good wash on some rapid stuff. It is like not really about it.
Yeah.
No, I tried to get them to talk to us. And then I was
yeah. Well, I know they're just really big into reuse, but I was actually talking to Devesh about how we have all of these engineers available, and like it might be a better idea for them to check with us first before they start sending the deal.
Jim, Chris, comes and because he saw somebody about something and then checked this. He's like, yeah, one of them was recording.
So they're, they're teaching from there. That's not good. That's not good.
Without checking with any of the engineers or any of the teams and stuff. Well, I'm not taking anything else, basically, whoever's manager's fault.
But at the same time, I mean, I think that it's really cool that, like, I mean, obviously I'm not in charge of, like, DLI or anything like that, but this is why CUDA was like, we need somebody to do inspection stuff to help correct shit like that. That's not okay. Like, and, we'll get there. We'll just get there. Because from my point of view, I'm just like, just make it better. That's all I want.
The tutorial that John is giving was nice. They're going to do some cuDF and some stuff. And they took the cuDF and stuff, or the one that I wrote for Python.
All right, let's go ahead and also, by the way, this is Jacob Tomlinson, the original author of this tutorial, and Natty. They'll be speaking during the conference. All right, so let's talk about this black and white example here. So first, all of our imports, just like we did last time. Load our image. Oh wait, hang on, I'm sorry. I don't have the answers pulled up. All right, imports. Here's our image, same one that we had before. All right, so we're gonna go ahead and move this over to the GPU exactly as we did before and set up our output. Same thing as we did here before. So in this case, right, we're looking at in the X and the Y direction, right? So a black and white kernel is a little bit easier than a blur kernel because we are not dealing with color, and it kind of is nice because it simplifies things a little bit for us. And so in this case, we're only looking at, in these two dimensions. So we have the X and the Y dimension. And same thing as before, where 16 by 16 is going to give us that, I lost my place, I'm so sorry. So yeah, our threads per block ends up being multiple. All right, let's go ahead and execute that.
There's definitely math. It would be 8 by 16, 16 by 60 is 256.
Yes, I was actually just doing that in my head, and I was just like, I'm not going to, okay, y'all are just a lot more attentive than, but I was like, that doesn't seem right, because I think I had, I think I actually changed that for a tutorial to show that you could use a different one and didn't change it back. I'm sorry. All right, so the black and white kernel here. So CUDA.jit, we have our same decorator. We are taking our X and Y indices, so using that CUDA.grid too. So once again, since we are not having to deal with color, it does simplify things quite a bit for us. Because our grid is slightly larger than our image, anything outside the image, we want to, we're going to ignore that and calculate the average across the RGB channels. So we take that average of red, green, blue. We're going to set out our output RGB channels to the average for all of them. So we've now set them to our grayscale. Okay, and then we are just passing through the channel. Okay, now we're going to go ahead and launch it and move it back. And now we have a gray numba logo. All right. I'm sorry that we're kind of running a little bit behind schedule. I think that, but the great questions. This is why this is so good, because we're getting good questions. But I'm going to try and pick up the pace just a little bit since we only have about an hour and a half left. We're going to still break in a few minutes for another break, but we're going to try and get through cuDF before we leave. So next thing I was going to going to mention was that if you do want to see what's going on with your GPU, one of the things that I think a lot of people are very surprised of when they start working with accelerated Python is that they'll start looking at their GPU utilization. They realize, oh my gosh, it's 0. Why is it 0? What is going on here? And they don't realize where things are actually executing, even though it may seem like they're faster or they're slower or things like that. Without having, dev tools to really help you dig in there, it's very difficult to tell what's going on. If you were to use the Jupyter Lab NV dashboard with this tutorial actually works with that. You would be able to look at GPU utilization, things like that, through the notebook. You do have access to all of these courses through our DLI platform for the next 6 months, just so you know. So you can come back to this and start playing around with it more and playing around with the GPU and doing some of the exercises or even try and write some more complicated kernels. There is a time limit that's on it. It's not like unlimited access to a GPU for 6 months, but at the same time, it is worth it to go back and do a little bit of experimentation, especially since we're not going to be able to get through a lot of these things like that. But yeah, all you have to do is install the NVIDIA ML-Py, and then this is going to go ahead and you can play around with this. So I recommend coming back to this notebook later and taking a look to see what your GPU is doing. Okay, next thing that we're going to talk about is the CUDA array interface. And I talked about this, I started alluding to this, that when we were walking through all of those different levels, when you start talking about the accelerated Python ecosystem, that there is a lot of interoperability here. And that array interface is really what makes that possible, okay? And so by working with something that is common across all of these different packages, we're now kind of creating the paradigm that allows us to move data more seamlessly. And it's not just in the sense that we're trying to move data in a way that the syntax is nice or in a way that we're very familiar with it, but also allows for implementation underneath the hood that is going to make it faster and make it easier for us to move things from GPU to CPU. When you're working with a CUDA array interface, you'll start seeing a lot of interoperability with things like tensors, as I mentioned before, working with PyTorch, working with DLPack, working with ND array, anything that has one of these array interfaces, you're going to see that makes it very easy to move across. And so that's why I think that one of the easiest, so coming out of numba, the reason that we would go to numba first is so you can understand kind of the internals of like what's happening in CUDA. You come out of that and you understand like we have threads and we have blocks and we have memory management that needs to take place, and I've run up against PCI issues, and now I understand that I have to launch a kernel and I have to be able to move all of these things around, right? Then the next point of entry, I think, is here at the array interface. So coming in at CuPy as being like the next major point of entry getting into the accelerated Python ecosystem, I think is the next place to go. And this is what's nice about this workflow, is that you would be able to do something like prototype your kernel in NumPy specifically, and then move it directly into CuPy. Just changing one import and see that as like your baseline of where you're starting. And that is a really good place to start. And it really is almost that easy. I helped someone at PyCon recently where all I did was change a couple of imports in their code, and they were doing all this image processing type stuff. And we had a 600 time speed up just from that without any other optimizations. So this is a good place to start. And so, like I said, using something like CuPy, NumPy and CuPy actually even will dispatch to each other. They can be aware of each other. If you call a function on a NumPy array, it'll call to NumPy. If you call something on a CuPy array, it'll call to CuPy. If you pass a CuPy array into NumPy, it'll automatically change it into a NumPy array. These are things that can be aware of each other and make that interoperability really easy. But what that also means is that you have to be extra special careful where you're executing, okay? And make sure that you're taking advantage of all of these memory management things that we've been talking about under the hood. And we're just gonna come at them in a slightly different way. Okay, So let's start looking a little bit at CuPy. And just want to mention, by the way, CuPy is an open source project. It's an affiliated project with NumFocus. Leo back there is actually a CuPy contributor. Hey, Leo. And but it is not an NVIDIA project, by the way. This is not something that NVIDIA owns. It is an open source project that came outside in the community. We work with the community, and we use it in code that we support, but it's not something that is like specific to NVIDIA. This is very much a community effort. And so let's take a look at what we're looking at here. So import CuPy as CP. We're going to instantiate a CuPy array, just random, just a bunch of random numbers in here. Okay. Bam, bam, bam. It's a lot of elements. It's good. All right. And you can see that this is actually in 3 dimensions, right? Even though we're specifying 1 as one of the dimensions. And then here, let's go ahead and pull up the type. And you can see that this is a CuPy.nd array. But you're going to see the syntax looks very, very familiar to what you're going to see in NumPy or anytime that you're working with anything that has that ND array interface on it. So let's convert this over to a numba array, which we saw before when we were looking at, we looked at the types on like the device array. We looked at different pieces when we were launching CUDA kernels from numba. So here, let's import CUDA from numba. And we're sending it over to the device. And then you can see here we have that device ND array. So once again, it's dispatched and it's gone ahead and done that conversion for us, depending on which level that we're moving to. So that's that interoperability that I'm talking about. And this is what makes it possible for you to do things like write kernels in numba and send them to PyTorch, or write kernels in numba and send them to CuPy, or do something, in CuPy and send it to PyTorch, or send it to cuDF. This allows for that sort of mix and match ability inside of this entire ecosystem. Okay, so we are going to import PyTorch here to show this. It's a bit of a large import, so it takes a minute. But here, what we're doing is we're going to create a torch array. So even torch as tensor, we're going to send over that numba device array, and we're telling it that it's a CUDA device array. We're specifying that, and then you're going to see that we now have a tensor object. And once again, so we've gone from PyTorch, we've gone to numba, we've gone to CuPy, we've gone to NumPy. Everything is the same. Same interface, different implementation under the hood. Make sense? All right. So let's go ahead and take a look at CuPy. I'm going to try and go a little faster. Let's see. Yeah, we're going to go through this one, then we're going to take a little break. So first, let's do our imports here. You'll notice that there's the CuPy CUDA.stream.null.synchronize. What this is doing, the reason that we call to the synchronize function is because when you're running things over on your GPU all at the same time, they may return at different times. Okay, there's nothing that's is synchronizing them on the other side. So especially if we're taking any kind of timing information and we want to show performance, we have to synchronize our threads and make sure that they've all quit running at the same time so that we can get a fair timing on it, right? So anytime that you want to synchronize your threads, you just call to this, and it's basically just gonna, we talked a little, somebody asked a question over here earlier during the break, and we were talking about streaming calls, which unfortunately we can't really get into, but basically what we're doing is that we're cutting it off, we're making sure that all threads are done executing when we call to synchronize. Okay, so from here, let's take some timing information. In this case, we're gonna do, we're creating a, right, so this one is actually gonna be on the CPU. So we're gonna create our arrays here on the CPU. All right, so 260 milliseconds, roughly. We're gonna time it here. Right, so we've gone from 260 milliseconds down to 7.88 milliseconds by moving over to CuPy. Okay. And then this is just a note about that synchronized function right there. Some basic operations, exactly. This should look very, very familiar to you if you've used NumPy. So any kind of broadcasting operations that you've done there, like multiplication and math operations should be the same, are the same syntax. So here, CPU time, we're just gonna, in place do a multiply by 5. And then on the GPU, multiplying by 5 in place as well. So here, hang on. The CPU time's 104 milliseconds, and this one, you saw that I ran it twice. I had to do that in order to kind of get it to get over that first initial cost. And then you can see that it goes down to 9.15 milliseconds.
And CuPy is designed to just-in-time compile everything, but it kind of like we talked about NumPy earlier. And so that's why that first run is so much longer, that it's doing that chip compilation first, and then every invocation after that, it hits a cache of that compiler.
Yeah. And for the video, I'll repeat that CuPy has just-in-time compilation built into it. So the first time we run it, it is doing a just-in-time compilation step. So you pay that tax that first time. Next time you come through, it is doing a lookup into the cache, and it uses the cache version of that function. Okay, so next one, we're going to do more math operations. So on the CPU, we're going to multiply by 5 in place. We're going to multiply 2 arrays by each other, and then we're going to add them together. All right, so 325 milliseconds over on the CPU, and then over on the GPU, we go down to 24.8 milliseconds. Let's go to some more complex operations. So in this case, let's do a singular value or decomposition from our linear algebra library. Yes?
So does it dispatch kernel each time, or does it kind of basically aggregate independent operations and actually just compiling maybe fuse operations just when we actually request things or something like that?
For this case, no, there's no fusion.
Okay, there's no fusion. This is just each.
Yeah. Each API there is an underlying kernel. Okay. But there are fusion capabilities.
Okay.
Yeah. All right, so from our linear algebra library, we're going to do a singular value decomposition here. So taking a two-dimensional random array, sending it over here, and then over on the CPU, we're at 1.21 seconds. And then over on the GPU, I'll run this twice, 368 milliseconds. So even you can see here, this is also just trying to show that we have, SciPy coverage as well, right? So CuPy is generally considered almost, not quite, but almost 100% compatible with SciPy and NumPy. So you can use both of those and the same syntax, the same library calls that you're used to using on NumPy arrays. Okay, so next one, let's go ahead and all right, so we're going to create our a CuPy random array here. And here you can see that we're actually going to be calling to NumPy linear algebra singular value decomposition. We're sending it a CuPy array. So let's go ahead and run this one. And all right. So I just want to point out here real quick that what happened, right? Why did this execute on our CPU? Anyone want to guess?
I assume in the CuPy array knows the operation and you can dispatch essentially CUDA. So it doesn't really run NumPy.
So this ran on our CPU, so it actually ran from NumPy, right? And the reason is because we actually specified NumPy here. So we went ahead and converted it from a CuPy array into a NumPy array and then had it run from NumPy. And that's the difference between calling it on the array and then sending it directly into the function, right? Because you have that ability to call as a method or as a function, right? And so this is the thing that I think people should mostly be aware of, right, is just being sure you know where you're sending it. Because especially when you do have that kind of compatibility and the APIs look the same, being clear and being very explicit about where you're running things as best as you possibly can to make sure that you're not missing any opportunities for better performance. Okay? Yeah.
So in the arrays we created in the GPU, and there is a GPU copy involved.
Right, so this array right here, we created a CuPy array. So this was actually created as a GPU array, and we sent it over into NumPy. So because we have that ND array interface implementation, it went ahead and did a conversion over to a NumPy array when we called np dot linear algebra singular value decomposition, right?
There's also some performance penalty.
Right, but if we had called it from CP here, right, then it would have stayed and it would have just executed on the GPU. Yes?
That's kind of what I assumed, but I'm a little confused about the timing. Why does it take as much time as running CUDA and keep on the GPU than compared to the logic around CUDA on the CPU? Does that mean, like, is it so much dominated by the random number generation?
I'm sorry.
I'm so confused. I thought both of those were running on the GPU because you explicitly say, oh, if you pass a GPU array to NumPy, it automatically runs it on the GPU. But you're saying that's not the case?
No, I'm saying in this case, we're sending a GPU array to a NumPy function, so that is actually in NumPy. So what I'm trying to say is basically that, like, you can, hang on, what is going on here? I'm sorry, Leo, did you have something you wanted to say real quick?
Yeah, I think we probably made a mistake when we made this material here. But I guess the confusion is why the timing looks a lot similar to the GPU execution. And the reason is that NumPy dispatches to CuPy in this case. So through this array function protocol. So we call NumPy assumption on the CuPy array. You look up that, hey, this is not a NumPy array, it's a continuous CuPy array. Then I dispatch, we use CuPy SVD in this case. And so this thing actually runs on GPU instead of on the CPU.
Oh, okay. Thank you. Yeah, sorry about that.
I don't think the opposite would be true because by design, you end up with the infinite recursion. So you have to start somewhere. And so the design of the array function protocol was that you want to do dispatching, you do it through NumPy. Right.
Thanks, Leo. Yeah, no, that's really good to know because we were.
We didn't catch the issue before.
Yeah, I'll fix that. This is good feedback. We'll get this done. All right, the next thing we just wanted to talk about real quick with devices. So you can have multiple GPUs available to you, and they do get a device ID. So if you have multiple GPUs, starting with device 0, they index just 1, 0, 1, 2, 3, whatever, and that'll switch between your different GPUs. So you can specify which GPU you want to use. The default is to device 0. If you only have one, that is the only device that it's going to go to. But you can switch between them by using a context. So using a with statement, you're creating a context, and we're saying that in this case we're going to use our device 0, and we're going to go ahead and execute there on that GPU. If you wanted to create a context for a different GPU, you just specify which device ID you want to send it to. And that way you're able to use both of them. I'm so sorry about this, hang on. And then let's go ahead and run this.
I think your position for a lot of time because it is like $3 from the time you launched the
Yeah, my Jupyter is messed up. Hang on. I'm going to take this off. You know what? This is a good time for a break. Let's go ahead and take a break. Okay, I think pretty much everybody is here, so let's go ahead and move on. Yeah, I think this is our last person that we need. Okay, so my Jupyter lab died. I restarted it. Here we are. If yours dies, also you can just go back to the DLI page and just restart it over here. But that's what happened for me, and so I restarted it. And so this example, just real quick, here we're specifying which device that we're going to instantiate this array on. And so here we have a random array that's being instantiated on device 0. And the thing is, when you query your actual array, right, you see which device it's on. This is just something to be aware of, that if you are creating a context and you're moving between GPUs, that probably not a great idea to allocate on one GPU and then move to execution on another GPU, right? You want to localize that data as much as possible. So making sure that where you allocate the data, where you have that array, where it's actually living, that's where you want to execute. So just kind of keep that in mind if you are switching between different devices. Okay, so where I was trying to get to was to this CuPy lab. So now is your chance to try it out yourself. And so, yeah, just give it a shot. It should be very, very similar to what you've done over in NumPy and SciPy. And don't forget to raise your hands if you have any questions. We will be coming around. I think we'll do about 15 minutes for this one. All right, just a few more minutes for this. All right, let's go ahead and go through this. So once again, the answers are in the next little notebook. So let's pull up the solutions. All right, first our imports. Create the input array with numbers 1 to 500 million. So just using a range or array range. And okay, now let's calculate how large the array is in gigabytes. And in this case, all we're doing is we're taking the number of bytes. So the same kind of interface you would see on a NumPy array. This is exactly the same. You would get the number of bytes off a NumPy array and dividing it by the size of a gig. So about 4 gigs. How many dimensions does the array have? Also the same as you would do in NumPy. So just 1. How many elements does the array have? Just take our size. So exactly what we would expect. What is the shape of the array? Same thing once again. And 1 dimension, exactly what we would expect. And so now create a new array with 5 million elements representing a linear space from 0 to 1,000. Once again, same interfaces we would use in NumPy, we just do linear space from 0 to 1,000, and then we specify the number of points that we want within that linear space, and it will create that for us. Okay, and so create a random array that is 10,000 by 5,000. All we're doing is sending in the dimensions. We've created a lot of random arrays at this point, so we're just sending in those dimensions and using the random operation on CuPy. And then sort the array, just calling out to sort. Looking good. All right, and then for extra credit, reshape the array to have 1 dimension, a length of 5. So remember that when you're reshaping it, it still has to represent the same amount of data. So even though you're moving your indices and you're kind of shaping it in a slightly different way to encompass the same amount of data, they still have to multiply together to reach the same number of elements as you had in your original array. So when we move 1 to 5, we just have to adjust the other other indices appropriately. So in this case, since we did have 10,000 by 5,000 up here, if we take one dimension and we reshape it to 5, we have to divide one of those by 5. So we could either do 2,000 by 5,000 by 5, or we could do 10,000 by 1,000 by 5, or any other combinations around there in order to have the same number of elements. And that's what we got.
The sorting, is there a difference between saying array equals array dot sort or CUDA sort array and just saying array dot sort?
Yes, actually. Let's see, which one are we calling to here? So, the best way to put it.
Since it is a CP array, you're assigning it back to itself anyway. You can just say ARR.sort.
Do you know if this one creates a copy? Because it is still producing a reference. It should. It does. Okay. All right, yeah, it's creating a copy. I wasn't sure about that, but yeah. And so when you're calling to an array.sort, it's usually doing it in place. So you're not having to reallocate any memory or do any kind of copying. In this case, it is creating a copy. And those copies, that's one of those things. I mean, just in programming in general, you try to reduce the number of copies if you can, depending on what kind of operation you're trying to do. Okay. All right. This next, I just want to mention this notebook. So nvmath-python is actually it's still in beta, but it's a fantastic math library for Python. So over on the C++ side, if you've ever worked with any of the X libraries or the CUDA-X libraries, there are dozens of math libraries that have everything, from low-level CUDA math, the FFTs, you got CUDA-en, you got all these other different things that are in here. But the thing that nvmath-python does, where there are dozens of libraries over on the C++ side, we've got one for Python. So this is the one-stop shop to get to everything that you need on the math side, which simplifies things greatly. So in one case, you're able to use all of the low-level CUDA math libraries, but you also have Python native implementations of very important functions as well. And obviously matrix multiplication and FFTs, I think, are probably the two most common math operations you can do in scientific computing. So those do have Python native implementations in them that are extremely fast and highly tuned. And then on top of that, I just want to mention, we did talk a little bit about the kernel fusion. So there are a couple of things in nvmath-python that allow you to do that. So you can add on epilogues, and you can also specify different functions that actually will get, on the compiler level, will optimize it for how to call into those different kernels, which I think is actually pretty amazing, to tell you the truth. So it will batch up different calls in order to reorder them in a more optimized way. And so having this ability is one of the things that's getting us closer to that performance that you would see on the C++ side from native Python. And so highly recommend checking it out. Like I said, it is still in beta. To get it working in here, the reason we're not going to go through it is just to let you know, you're going to have to switch CUDA kernels. So you actually have to come over here and switch to a different IPython kernel. So the nvmath-python kernel will be the one that you need in order to be able to run it. And so we're just not going to do that this time. But in case you do want to go through it, that's the one that you have to use. And it's just because the dependencies were a little bit weird when we put this in here. It'll be working just fine in the next version. But just give it a shot and see what you think. Okay, so with that, we're going to go ahead and move over to cuDF. I think that, as I've been working with the Python community a little bit more, especially in the last year, I find that most people, their introduction to any kind of GPU computing is either through PyTorch or cuDF. That they've done either a ton of work with pandas and they're doing something, or they're working in deep learning somehow, and that's how they're first learning about CUDA as a programming paradigm. And so cuDF obviously is kind of our drop-in replacement for pandas. It is very, very hard to replicate every single thing about the pandas API. I don't know how many of y'all have ever tried to teach a class on pandas like I have, and there are about 10,000 different ways to do something, and it has a very, very huge API, and covering the whole thing is almost impossible. But this comes as close as possible to being able to mimic all of the syntax for pandas. So a lot of these examples should look very similar to what you would expect when you're working with pandas. So first, let's import cuDF. We're going to import pandas. Okay. So for this one, we're going to go ahead and pull in the CSV that's included in here, just so that we have a decent amount of data to work with. In this case, I believe this data is looking at Wikipedia pages and what language they're in. I think that's the data set that we're working with. And I kind of mentioned before, like when we were working with FizzBuzz, that working with strings in CUDA is a little bit dicey. The reason that we, had suggested you use 1, 2, or 3 is because strings can be variable lengths, right? And we have to specify exactly how much memory we're using over on the GPU. So working with strings can be a little bit strange because, you're not really sure exactly how long your string is going to be, or you have to, all those things like that, right? So once again, using something like cuDF, which has a nice interface to using strings, it's using cuString underneath the hood, and it allows you to work with strings on the GPU without driving yourself, totally crazy trying to figure out how to handle fixed length strings. And so highly recommend going this route if you're working with a lot of string data or categorical data. And so, all right, so we've pulled in the CSV. From here, we're going to do the same thing from cuDF, and we're going to pull in the CSV here. Should look exactly the same as you would expect. Let's see, yeah, so this is the 1 million records of page view counts from Wikipedia in various languages. So the first thing that we're going to do here is let's rename the columns and drop the unused X column. So page views.columns, we're going to specify project, page, and requests, and X are our indices, and then we're going to drop the X and take a look at what we've got. So now we have our project, the page, the requests. So we have successfully rearranged our data a little bit. Okay, next thing we're going to do is let's count how many English records there are in this data set. So we take our page views, .project is going to be equal to EN for English. And so that's going to select all of our English records. We're going to pull those out of the page view data frame, and then we're going to count them. Okay, understand how we got to that? So this is where we want doing the select. We use that to index into our page views data frame, and then we're going to take a count on that. Okay. Sometimes when you start building these up on pandas data frames, it gets a little confusing what's going on. But from here, we get our count. Yes. Page views, project count. Okay. Now let's perform a group by where we count all of the pages by language. So in this one, we're creating a group by object instead of doing a select. And so here, this is the group by object. That's going to group by project. We take the count, and we're resetting the index. And the reason that we're resetting the index is so that we can get this for each of the, for each language. All right. Group by project, number of counts, and reset the index. Yep. So this gives us a number of pages, number of requests, and by project. Bam. These are not very friendly names in here. Like, wow. That's a little, do you want to talk about ss.m or vec.s? So anyway. All right. And now let's have a look at the results for English, French, Chinese, and Polish. So same thing we did before where we're doing a select and we're going to take the is-in function here to look in this list of different languages, and we're going to pull those out. All right, so for French, Polish, that's Chinese, and English, we have the number of pages, number of requests. If you have used pandas before, then all of the syntax should be very familiar to you. In the same way that CuPy implements a large portion of NumPy, CuPy implements a large portion of pandas. The only difference is that all of our filtering and group by operations happen on the GPU instead of the CPU, which is what gives you that better performance. I know that this is not extremely scientific or anything like that, but generally when people ask me, like, where do I start seeing a big improvement using cuDF? I'm just going to tell you that through my trial and error experience, like generally around 8 gigs is where you're going to start seeing real improvement in your performance going from pandas over to cuDF. And I also do want to mention that people always ask about polars, and so cuDF is also working with the polars team. So if you are working in polars, there is the possibility of being able to use a cuDF backend for that as well. So it's not just specifically for pandas. cuDF is also working with polars. So back to strings. All right. Mentioned this a couple times now, but GPUs historically are well known for their numerical work, not so much with their string work. There are string operations that are accelerated to, they have specialized kernels that work specifically with strings. We can do things like string operations on our data frames here. So for here, we're going to take our page to string, and then we're going to make it uppercase. So just uppercase for everything here. And then same thing down here, we're going to take our projects that are in English, and then we're going to take the page, the string representation of the page, and we're going to take it to uppercase, and then we're just going to look at the first few rows. So this is what we have. Okay. Okay, so user-defined functions. We talked a little bit about functions in the context of numba, but the same thing happens over in pandas. I think one of the most powerful portions of pandas is to be able to define your own functions and pass them in. And if any of y'all have ever done any kind of like user-defined functions in pandas and you're using like NumPy or something like that, very similarly over here on the GPU side of the world, we're doing the same thing. And you can think of these user-defined functions as kernels. So we're really creating a kernel that's going to run on our new GPU version of the data frame. And we're going to use the same kind of API that we use over on the Pandas side. So you would call to apply in order to send over your user-defined function. We're going to do the same thing here, and that's what's going to launch our kernel for us over on the GPU. So here, let's define a user-defined function here. If an element is less than 5, we're going to return 0. Otherwise, we return the element. So it's just a mask to mask everything out that's under 5. And then we're going to take our page views, and everything that's under 5 should be masked out and just go to 0. All right, so you see a bunch of zeros. There you go. All right, so It's also possible to use numba directly to write kernels and then take a pointer to the input column and the output column along with additional arguments. The kernel can then use CUDA.grid the same way we did in the chapters 1 and 2 and get an index to operate on. We then use for all to map our kernel over a column. So in this case, what we're going to do is we're going to create our page view. In our page view data frame, we're going to create a new column called mul requests and initialize it to 0.0. So that's the first thing we're going to do. We're going to import CUDA from numba. I'm going to JIT this user-defined function. So here we're specifying multiply. So we mentioned that we're going to take the pointer to an input column. We're going to take a pointer to the output column, and then we're going to take the multiplier here, right? So as we move through, we're going to multiply by whatever the multiplier is that you pass in. So in essence, it's kind of like, broadcasting a multiplication, but we're going to move across the entire grid. So this is also, by the way, I just want to mention only for one dimension since we do hard code the 1 in here. So just to be careful of that, it's not completely generalizable. It is very specific to a one-dimensional. So let's go ahead and define our function. And then we're going to call multiply for all. Okay, this is a lot all up on top of here, right? So we're going to take our input column is the page views requests. So we're going to pull out the requests. Our output is the multiplication request that we had initialized to 0.0. We're going to multiply by 10. And then we're basically just saying that this is for the length of all page views. So we're going to use this for every single element inside of our data frame. Does that make sense? That's a lot of syntax right there all together. Okay. But yeah, this is really, this is our JITted function. We're taking basically all of these page views here, and then we're going to, here's our calling arguments right there. So we're just going to multiply everything by 10. Okay. So multiply by 10, and then let's, yes?
So based on the for all the n of pages, it's going to figure out the blocks and threads automatically behind the scenes, or multiply or
So the for all is the thing that we use to map this function across our data. Does that make sense? Yeah. So this is what's going to make it. We're mapping this kernel across all the data inside of the data frame using for all.
It's going to say whether we need 128 threads or that thing is going to be.
Right. So yeah, that was hidden from us, right? That's one of those cases where now that we're in a higher level library, it's abstracted away the need for us to understand and define exactly what that the threads, number of threads and blocks and things like that. But we are still handling the indexing, right, with that grid function. But a lot of the other pieces, like I said, they're just kind of handled for you, which is one of the nice things about using a nice interface like this. Okay, so we multiplied by 10, and now you can kind of see here, we're only taking the first few of the elements, so not particularly exciting because they're all 0. So multiplying by 10 is going to give us 0 again. Probably need to find some that have a different one. All right. Very important to be able to do rolling windows. Everyone who's ever taken a rolling average, this is where it really comes into play. I know that, especially back when I ran a data science team, that rolling windows were one that we used quite a bit, especially anytime we had any kind of adaptive features that we used in any of our machine learning models. You have to be able to look over either a time series or look over, other values that lead up to that one. And so here, you can think of this as basically we have the window here, And then where we're going to put the answer to that particular window is going to be at the last element within the window in our output array. And so you do have like a little bit of a gap that happens in here. And it's just something to kind of keep in mind because we do have fixed length memory allocation on our GPU. That's like a remnant of that, basically, in order to get the indices to match up with each other, so you know exactly like where that answer is for that rolling window. That's where we have to put it. Okay? And so let's take a neighborhood mean. So we're going to define our neighborhood mean function. We're setting in our window. So, all right, we're initializing our answer here to 0 for each value within the window. We're going to add them up and put them into C, and then we're going to take the average. So by dividing by the length of the window, right? So we're adding everything within the window, taking an average. Oops. Let's go ahead and define this function. All right, so page views dot requests dot rolling, and so rolling is the function that we're using here. And we use apply as what's going to actually launch our kernel, right? So that's the user-defined function. That's our kernel that we're going we're actually computing with. So we're passing in our neighborhood mean here. And then so rolling, all we're doing here is we're specifying the length of our rolling window, the output, and then I forgot what the true stands for, but basically it's just taking that rolling window and we're going to apply that particular function onto the window. And so that's how we call it. And I think this is also not particularly fun because it is all zeros. Yeah, probably need to find some actual values in there to make it more interesting, but it is mathematically correct. All right. Okay, so I know we rolled through cuDF very, very quickly, and we fortunately have Keith in the room. So what are your questions about cuDF before we move on?
We'll just add, we talked a lot about user-defined functions here, and if you look at maximize your performance, use the built-in functions whenever possible. Oftentimes, the built-in functions have different heuristics and things like that that allow us to better parallelize them with the underlying GPU and will run multiple times faster than user-defined functions. And so, in this case, being able to do kind of like a rolling window mean, I'm pretty sure there's a built-in function for that. Obviously, this was just to demonstrate GPX. Use the built-in mean because it would probably be an order of magnitude faster than the user-defined function.
Yeah.
The way they can actually map it onto the underlying blocks and threads of the GPU is going to be different than how they would map it via user-defined function.
Yeah, and just to reiterate that for those, especially on the video here, this is the rule of thumb that I tell people, and I mentioned this in my GTC talk and everything, that generally when you're working in this accelerated Python ecosystem, try to stick with the highest level library that you can and try to find, implementations that are already written for you and move lower if you're not finding what you're looking for, basically. There are many, many, many paths to success, which you're probably picking up on since you can see so many different ways for us to do any of these problems, actually, that we've been going through. And especially with the interoperability between different libraries, there are a lot of different ways to go. But as Keith was talking about, there are some very, very common use cases that people have thought through very deeply and have very optimized versions of functions available to you that are like kind of the first place to start, I feel. But if you do need to go deeper and you do need to write your own kernels, not to be afraid of it because you have those concepts up in your mind as long as you remember the memory model and you got your numbers of threads, your numbers of blocks, making sure that you're being very careful about your execution, how many times something executes and where you're putting your output. All of those concepts are going to work on any single library that has low-level CUDA access. Okay? And so that is where I'm going to end, actually. There's another one in here that I think you might enjoy looking at, cuML. If you're interested in scikit-learn, this is comparable to that. So very similar interface, a lot of drop-in replacements available here over on the scikit-learn side. And then also, if you are interested in Dask at all, we obviously can't really get this up and working in our Deep Learning Institute platform, so it won't actually work for you. But if you are interested in at least reading about Dask, this is a decent amount of information here, and it points you to some nice resources as well. But with that, I really just kind of wanted to reinforce what we talked about here, okay? So when we looked at this at the very beginning and you were looking at this whole, like, this is your toolbox, if you want to think of it this way. There are a lot of different libraries that are available to you. And this is actually only just a subsection of all of the libraries that are actually available to you. The toolbox is huge. Understanding, like, where are the points of entry? I think the first one that is the most important one is CuPy that I mentioned here. So CuPy, if you have ever used NumPy, and NumPy is the basis for everything that we do over on the scientific stack, you can use CuPy. So that's the first point of entry, I think, for most people to understand what's going on. Second one would be PyTorch, which is very, very high level, but at the same time very popular right now and does have low-level CUDA access into it, but it's using tensors. Because of the use of tensors and that ND array interface, you can use any of those other libraries that we mentioned in order to interact with it. So you can write your own activation functions, for example, and be able to point and move those into PyTorch. Another one is Rapids. Rapids is a really, really easy one because if you've ever used scikit-learn, you use cuML. If you've ever used pandas or polars, you use cuDF. Those are, or NetworkX, you can go to cuGraph directly. So this is a very, very easy transition. And then if you're moving a little bit lower into the stack, you really do start getting into launching kernels and writing kernels yourself and handling a lot of that memory management yourself. Like I said, each one of those concepts, totally universal across all of these. Defining your threads, defining your blocks, making sure that you're optimizing the number of copies and you're not creating bottlenecks across your PCI bus. And for all of those things, especially on the low level, make sure you're using your Nsight tools because print is not going to get you as far as you think it might. Okay. All right, that's a lot of rules of thumb. Let's have like 10 different thumbs. But that is kind of the overview of what hopefully makes sense here. And I really just want to remind you that there are a lot of good things available out here on this repository. So the Accelerated Computing Hub is definitely a nice resource to use. Like I said, it's my repository. Anytime you open an issue, if you put in a PR, whatever, it goes straight to my inbox. I will hunt down the person for you who can answer your question. I've tagged Leo on questions before. I think I've tagged Sergey on a couple of questions. This is meant to be a way for us to talk to you. And we want people to be able to understand this, and we want to make it better. So also feedback is welcome. So please, you're finding something very counterintuitive. Feedback is, I think, also very, very valid. So do not be afraid to reach out to us. And then I promised at the beginning of this that I would put this code back up here. But this code is good for a free Deep Learning Institute course of your choosing. We did go ahead and extend it so that you're able to access the course for up to 6 months. So you do have access to everything that we went through in this particular course through the DLI that you use today. It should show you as being enrolled in the course. You have access to it for the next 6 months. This gives you access to anything else we have over on the Deep Learning Institute website. So if you want to learn more about kernel authoring or LLMs or, diffusion models, anything that's out there. You're welcome to choose anything of your choosing, and you will also have access to that for 6 months as well. And please also, if you do have time, everyone got that code? Who wanted it? Okay. If you don't mind, coming over here to the feedback portion of this. Unfortunately, this is actually the last time we're going to be using this this material for this tutorial. So, but I would love to hear your feedback on this course. Tell me what's working for you, what's not working for you, what could be better, what could be, what really hit home or resonated with you. And we will take that into account moving forward. All right. Thank you so much for attending.